How did early humans interpret and find meaning in the night sky? How did people use the stars for navigation before maps and compasses existed? On a clear, moonless night, long before cities ever existed, a small group of our ancestors gathers beneath the open sky. The world around them is dark and still. Above, an endless canopy of black stretches from horizon to horizon, pierced by thousands of shimmering stars. In the crisp night air, the stars seem close enough to touch. Each pinpoint of light flickers gently, as if whispering a secret. They sit in silence around the glowing embers of a fire, eyes turned upward in quiet awe. They have no words like galaxy or astronomy, but they feel the majesty of the night sky deep in their bones. Perhaps they wondered if the sky was a great dome overhead, and the stars were holes in it, letting through light from beyond. Or maybe the campfires of gods scattered across the heavens. In the dream time of Aboriginal Australian tradition, for instance, the night sky's lights were seen as campfires of ancestral spirits, and the Milky Way as a great river of souls flowing across the heavens. Under that vast spangled tapestry, those early people might have felt both very small and deeply connected to something immense. The night sky was overwhelming, yet somehow comforting, a constant presence that cycled night after night, reliable as the sunset and mysterious as a dream. As the fire crackles softly, an elder in the group could have raised a hand to trace patterns among the stars. Human eyes naturally seek shapes in chaos, and against the clutter of lights, they began to find familiar outlines. Perhaps one cluster of stars resembled a hunter chasing an animal, while another grouping looked like a resting bird. These first imaginings were the seeds of constellations, pictures in the sky to help make sense of the sparkling chaos above. In sharing stories about these starry shapes, early people found meaning and companionship in the night. The sky was no longer just a random scattering of lights. It became a canvas for stories, a map of legends spread out above the world. Without modern distractions, the ancient nights were unimaginably dark, and the stars astonishingly bright. Uncountable stars crowded the sky from one horizon to the other. Some glinted with a cold, blue-white sparkle, others with a softer golden or reddish glow, a subtle celestial rainbow sprinkled across the darkness. The Milky Way band glowed like a pale river of mist overhead, so vivid that it cast faint shadows on the ground. You can picture those distant ancestors gazing at that ghostly band of light, perhaps believing it was the smoke of their campfires rising to the heavens, or a pathway for spirits to travel. In that age, to look up at the night was to witness the full grandeur of the cosmos in a way we rarely experience now. Every speck of light in that river of stars called out to their curiosity. Over time, this awe of the night sky took root in human culture. The heavens became a source of guidance and a source of meaning. We can imagine people across different lands, all looking at the same sky with a similar reverence. In every corner of the world, from open plains and deserts to thick forests and high mountains, people turned their eyes upward. They noticed that the same star patterns would return each year at the same time, marking the passage of seasons. They watched reddish wanderers like Mars and bright morning stars like Venus move against the background of fixed stars, and these observations must have stirred questions. What are these lights? Why do some roam the sky while others remain eternal? To the people of long ago, the sky was alive with possibilities. Some stars never seemed to rise or set, circling endlessly around a fixed point in the north. These unsetting stars felt eternal. In ancient Egypt, for example, Two such stars near the North Pole were called the indestructibles, seen as symbols of immortality because they never disappeared below the horizon. Many cultures came to believe their gods or ancestors lived among those undying stars. High above the transient world of Earth, the night lights were constant and pure. Watching them, our ancestors sensed the presence of the divine or the eternal looking back. Even without understanding what stars truly were, people tried to get closer to the sky's mystery. They built structures aligned with celestial events, merging earthly stone and the heavens above. Great circles of standing stones and carefully arranged pillars tracked the rising of the sun, the phases of the moon, and the return of certain stars. In a grassy plain, a ring of stones might frame the point on the horizon where the brightest star of winter first appears at dawn, signaling that a new season is at hand. On distant hilltops or in desert sands, monuments were erected so that on a particular night, starlight would shine through a special opening, marking a sacred day or guiding ritual celebrations. Each of these ancient observatories was a testament to the profound connection felt between humanity and the stars. The earliest recorded stargazers left subtle traces of their fascination. Tens of thousands of years ago, someone carved dots and symbols into a piece of mammoth ivory, possibly a map of the stars overhead. In a silent cave, an artist painted a cluster of 7 dots on a rock wall, reminiscent of the Pleiades star cluster that even today sparkles in the autumn sky. In later ages, as civilizations grew, people even crafted the image of the sky into lasting artifacts. A bronze disc buried for millennia in European soil was found adorned with gold symbols of a shining sun, a crescent moon, and a cluster of tiny stars, a cosmic snapshot preserved in metal, perhaps used as an early calendar or a sacred map of the heavens. Those delicate clues tell us that as far back as we can trace, humans were mapping the heavens in stories and art. The night sky was humanity's first and oldest storybook. Night after night, generation after generation, people watched the skies. Parents pointed out familiar stars to their children, who one day would do the same for their own. You can almost see a mother or father kneeling beside a curious child, drawing shapes in the sky with a finger and whispering the ancient names of the stars, passing on that sacred knowledge. Around flickering fires, stories were shared of how the world began under these stars, of gods and heroes placed in the sky long ago. There was comfort in these shared visions. No matter how uncertain life on Earth was, whether food was plentiful or scarce, whether tribes wandered or settled, the stars were always there. They rotated overhead with patient regularity. They faded with the dawn and returned with each twilight. They were faithful companions in the solitude of darkness. Under that primeval sky, it didn't matter that no one yet knew the true nature of stars. What mattered was the feeling they evoked. The night was a vast, mysterious realm, but not a frightening one when understood through songs and myths. The sparkling dome above was a grand stage where the imagination could roam freely. For early humankind, simply watching the heavens was both entertainment and enlightenment, sparking questions about creation, existence, and the beyond. In those first moments of wonder, when a person tilted their head back and truly saw the stars in all their glory, something changed forever. We became aware of the enormity beyond our daily lives. Our minds began seeking patterns, meanings, and stories up there among lights that would outlast countless human lifetimes. This was the birth of astronomy in its most basic form, not a science of equations, but a human longing to understand the universe. Beneath the canopy of stars, humanity had its first profound conversation with the cosmos, a silent exchange of wonder that continues to this day. The hush of that ancient night lingers in our collective memory. Even now, when we stand under a quiet sky far from modern life, we can feel a little of what our ancestors felt. The same spark of awe lights up inside us. We too are moved to pause and breathe deeply, to take in the glittering infinity overhead. The legacy of those first stargazers is that we have never stopped gazing upward in wonder. That enduring awe, born in prehistory, laid the foundation for everything we would eventually learn about the stars and beyond. The same stars that enchanted our ancestors would soon guide them as well, leading wanderers and explorers across unknown lands and oceans. The heavens, that were once purely a source of wonder, became a trusted map by which to navigate the wide, mysterious world. The ocean is calm and endless under a moonless sky. Imagine yourself as an ancient mariner on a small voyaging canoe, gliding over gentle waves in the dark. There are no maps or compasses on board, only the stars above to guide you. The night air is warm and salty. All around, the horizon blends into the starry sky, so that you seem to be floating in a vast bowl of darkness sprinkled with light. Overhead, familiar constellations slowly wheel. Despite being surrounded by open sea, you feel a reassuring sense of direction, because the patterns in the sky tell you exactly where you are and which way you must go. It is as if those distant lights are your companions, silently pointing the way forward. For thousands of years, people ventured into the unknown with nothing but the heavens to lead them. The stars became a trusted compass. Early navigators learned to read the sky as if it were a map drawn in light. Each star's rising and setting point on the horizon was noted and remembered. On the open ocean, far from any landmark, a navigator could align their canoe with a certain star at dusk and know that following its path would carry them toward a distant island. When that guiding star set in the west, they would choose another rising in the east, maintaining their course through the night. In this way, entire pathways across the sea were charted in the mind, using sequences of stars like stepping stones across the sky. Consider the Polynesian wayfinders, perhaps the greatest natural navigators in history. In a time long before modern instruments, they sailed canoes across vast stretches of the Pacific Ocean, from one tiny speck of land to another. A Polynesian navigator, awake under the glittering night, knew dozens of stars by name and precisely where each would emerge and disappear along the horizon. He could feel the pattern of ocean swells and the caress of the wind on his skin, but it was the sky that was his surest guide. If he wanted to sail north, for instance, he might watch the star Hoku Pa, the North Star, hanging low over the ocean, and keep it at a constant position relative to his canoe. To head eastward, he might wait for a bright star like Hoku Lea, Arcturus, to rise at a certain point on the horizon, then follow its ascent through the night. Through careful observation and knowledge passed down from teacher to student, these wayfinders carried a mental star compass. The night sky was divided into houses or segments, each defined by the rising and setting positions of key stars. By knowing when and where a star would appear, they always knew the direction of home or the direction of their destination, even after weeks at sea under ever-changing skies. It wasn't only in the Pacific that the stars guided explorers. All over the world, travelers turned to the night sky when they needed to find their way. In the Northern Hemisphere, sailors learned to find Polaris, the North Star, which gleamed in nearly the same spot every clear night, barely moving as the other stars wheeled around it. By keeping Polaris directly ahead or directly astern, they could sail north or south with confidence. The height of Polaris above the horizon even told them how far north or south they had ventured, a starry gauge of latitude known long before modern instruments. Viking seafarers crossing cold northern seas and Arab traders journeying down the African coast both relied on that constant northern light to stay on course. On land, desert nomads crossing vast dunes at night would orient themselves by the stars as well. Imagine a caravan trekking through the silent Sahara under a dome of brilliant stars. The sand is cool beneath the camel's feet as the day's heat fades. The guide at the front pauses on a dune crest, looking up for a sign. There, the Big Dipper comes into view above the northern horizon. He traces its 2 pointer stars down to the dim glow of Polaris. With a quiet gesture, the guide adjusts the caravan's course ever so slightly so that the North Star stays at the same spot over his right shoulder. In this way, even without landmarks in an ocean of sand, the travellers keep moving steadily toward their destination, guided by that constant pinprick of light. In the southern hemisphere, where there is no bright pole star, travellers looked for a cross-shaped cluster of stars, the Southern Cross, and drew an imaginary line through it to locate south. No matter where people journeyed, there were stars above to give them direction. Picture a small wooden ship in ancient times, its single sail filled with wind as it leaves the sight of land behind. At twilight, the navigator watches the first stars peep out one by one. Perhaps he smiles as he recognizes a bright star, exactly where he expected it to be on the horizon. All night long he will stay on deck, checking the positions of the stars and gently adjusting the ship's course. The crew sleeps below, but the navigator remains awake with the sky. He has spent years learning the movements of these stars, how one star will rise a little farther south each night as the seasons change, or how another star, once high overhead at the start of the voyage, will sink lower night after night as they travel toward new latitudes. With this knowledge, he can tell not only direction, but roughly how far they've come. The stars are his clock and compass together. There is a deep comfort in this routine. As long as the familiar stars continue to march in their expected paths, all is well, and the ship is on the right course. The navigator might even hum an old song under his breath, perhaps a song that names the stars in the order of their appearance. A lullaby learned from the elders that doubles as a precise navigational chart. Over generations, the techniques of celestial navigation grew more refined. Ancient Greek and Phoenician sailors made detailed star charts and could predict the best times of year for sailing certain routes by the stars. By medieval times, scholars and seafarers had developed instruments like the astrolabe and quadrant to measure star altitudes, turning the art of navigation into a science. Yet even with these tools, the essence remained the same. By looking up at night and understanding the sky, travellers found their way. A captain standing on the deck of a ship in the 15th century, determining his latitude by the angle of Polaris above the horizon, was using knowledge that had been passed down since the age of simple canoes and desert caravans. For those who knew how to read it, the sky was a reliable friend in the unknown. It meant freedom to explore. Thanks to the stars, humans voyaged to new continents, carried by curiosity and the constant glittering guidance above. Each journey under the stars also reinforced a feeling that the universe was watching over them, that the lights in the sky cared for their safe passage. When sailors spoke of a guiding star, they often meant it quite literally, a star that would lead them home. There is profound poetry in that. A tiny point of light, so far away, could determine the fate of people on Earth and give them the courage to venture farther. And as much as the stars guided footsteps and rudders, they also guided minds and spirits. The sky's practical uses did not diminish its mystery. If anything, they enhanced it. A navigator might offer a prayer of thanks to the stars before a long voyage, treating them as guardians in the night. In many cultures, the boundary between navigation and reverence was blurred. The stars that formed a map were also celestial beings with stories of their own. The same North Star that kept a traveller on course might be seen as the watchful eye of a deity above. The sky that served as a compass also became a great cosmic storybook. The constellations overhead turned into legendary heroes, mystical creatures, and gods shimmering in the darkness, each with a story to tell. Guided by both curiosity and imagination, people connected the dots of stars into pictures and wove meaning into them, filling the night with myths as infinite as the stars themselves. All across the world, people have looked at the same stars and imagined very different things. To an ancient Greek gazing up, a cluster of stars might form the outline of a hero fighting a bull. To a fisherman in the South Pacific, those same stars might be a giant canoe riding the heavenly ocean. The night sky became a mirror of human culture, reflecting each society's myths and values. Constellations, the patterns people connect among the stars, were like ink blots in the sky, shaped by the stories told beneath them. And so the heavens filled with legend. Every sparkling group of stars held a tale. If you lie back under a clear night and let your mind wander, you can start to see the figures our ancestors saw. Over there, 3 stars in a neat row form a belt strapped around the waist of a great hunter. Above and below that belt, other bright stars sketch out broad shoulders and sturdy legs. This is Orion, the mighty hunter of Greek mythology, striding across the winter sky. In Greek lore, Orion was a fearless giant, said to be the most handsome of mortals and a peerless hunter. He roamed the forests with his bow and sword, boasting he could slay every beast on earth. According to one legend, the earth goddess sent a small scorpion to punish Orion for his arrogance. One bite on his heel was enough to bring down the great hunter. Eventually, the tale goes, Orion met his fate from the sting of that tiny scorpion. The gods placed Orion among the stars, with his shining belt and sword, so that his bravery would be remembered for all time. To keep him humble, even in death, they set the scorpion in the sky as well, as the constellation Scorpius on the opposite side. So the hunter and the scorpion never meet again. And trailing behind Orion, the brilliant star Sirius, the brightest of all the night stars, was said to be his faithful hunting dog, forever following his master across the heavens. On crisp winter nights, when Orion's form sparkles high above, storytellers still point out his belt and shoulder stars, recalling how even mighty Orion was humbled, and how he now keeps eternal watch in the winter sky. Not all cultures saw a hunter in those stars. Far to the south in Australia, some Aboriginal peoples looked at Orion's pattern and saw a young man, or hunter, with a very different story. In one Yolngu story, the 3 stars of Orion's belt were 3 fishermen in a canoe, and the faint stars nearby were fish they had caught. Meanwhile, in China, that same group of stars was sometimes seen not as a person at all, but as part of a large white tiger prowling the heavens. It's fascinating how the human mind can connect the same dots in such creative ways, weaving stories that reflect local landscapes and traditions. High above our heads, wheel the great circles of the constellations, carrying an entire library of folklore. One of the most universally recognized patterns is the Big Dipper, 7 bright stars forming the shape of a ladle in the northern sky, part of the larger constellation Ursa Major, the Great Bear. Many people today know it as a guide to finding the North Star, but to our ancestors, it was rich with meaning. In North America, several Native American tribes saw those 7 stars as a great bear being pursued by hunters. The 4 stars of the bowl made up the bear's hindquarters, and the 3 stars of the handle were 3 warriors following behind. As the seasons passed, the bear appears to run across the sky with the hunters forever in pursuit. In Europe, those same stars were imagined as a plough, or as King Arthur's wagon rolling along the heavens. In ancient China, they were known as the Northern Dipper, seen as part of a celestial bureaucrat's chariot or a divine measuring scoop. It's amazing to think that one simple pattern of stars has inspired such a variety of tales and names. But whether it was a bear, a wagon, or a plough, people everywhere found familiarity in that collection of stars and made it their own symbol. Sometimes, different cultures came up with surprisingly similar stories for the same stars. Take the Pleiades, the little cluster of faint stars that adorns the shoulder of Taurus the bull. On a dark night, you can see 6 or 7 of those tiny stars gathered close together, like a sprinkling of cosmic dust. The Greeks called them the 7 sisters, and said they were the daughters of Atlas, placed in the sky for their protection. Many Native American peoples also envisioned those stars as a group of sisters or girls. One story from the Kiowa tribe tells of 7 young girls who were chased by a bear. To save them, the Great Spirit raised the ground under their feet to the sky, creating the stars of the Pleiades. And the story says the lifted ground became Devil's Tower, a tall rock formation, but that's another tale. Even in distant Australia, Aboriginal stories speak of the 7 sisters as a group of young women fleeing a relentless pursuer. It's a testament to the shared human imagination that cultures separated by oceans all looked at this delicate cluster of stars and sensed a similar theme: a tight-knit family eternally together in the night, often being chased or protected. Not all star myths were about heroes and battles. Some were gentle lessons or romantic tales. In the starry firmament of ancient China, people could pick out 2 particular stars on opposite sides of the Milky Way and tell a love story. One star, a bright white beacon known as Vega in the west, was Juno, the weaving maiden, and across that silvery river of the Milky Way shone Altair, Niu Lang, the cowherd. In life, legend says, these 2 fell deeply in love and neglected their duties in heaven. As punishment, they were placed in the sky as stars separated by the great river of light, able to see each other, but forever apart. Yet once each year, on the 7th night of the 7th lunar month, magpies take pity on them and form a bridge across the Milky Way, allowing the lovers to meet for just one precious evening. On that night, known as Kishi in China and later celebrated as Tanabata in Japan, people would look up at the sky and hope for clear weather. For if it rained, it meant the lovers' tears were falling. This tender story of the weaver girl and the cowherd gave the summer stars a poignant meaning. What might otherwise be just 2 bright points of light became a reminder of devotion and longing. Even told softly, it's a tale that can touch the heart. For generations, it imbued those stars with special significance each summer. A yearly reminder that love bridges even the widest of gaps. Every culture has its celestial fables. The ancient Egyptians identified the star Sirius with their goddess Isis, and when Sirius rose before the sun at dawn each year, they believed it was Isis heralding the life-giving flood of the Nile. In India, the steadfast pole star, today's Polaris, is personified as Dhruva, a devoted boy in Hindu mythology who was granted immortality in the sky. The Maori of New Zealand celebrate the rising of the Pleiades, which they call Matariki, in June as the start of their new year and a time of renewal, complete with legends about those stars bringing good fortune for the coming year. From the Norsemen, who imagined the god Odin striding among the stars, to Hindu storytellers who saw the Milky Way as the sacred river Ganga flowing in the heavens, the sky has been a canvas painted with every hue of human belief. What is truly enchanting is how these star myths gave people a sense of connection to the cosmos. When they looked up, they didn't just see burning spheres of gas, a fact unknown to them. They saw family members, gods, animals, and heroes shining down. The night sky became a great stage, and the stars were actors in stories that explained the world and imparted wisdom. These tales often carried gentle morals or served as comforting reminders. A parent could point to a constellation and reassure a child, "See those stars? That's the great hunter watching over us." Or, "Those are the 7 sisters, always together, just like our family." In this way, the cold, distant lights became warm and familiar. Gathered under the blanket of stars, communities felt the presence of their legends living in the sky. The constellations gave them seasonal markers for planting and harvesting, yes, but they also gave them companions through long winter nights and cosmic guides that meant more than mere navigation. They were cultural compass points. Each glittering figure overhead was a repository of memory and meaning, reminding everyone around the evening fire of who they were and where they came from. As you imagine those ancient nights, you can almost hear the murmur of an elder's voice, weaving these tales in the darkness, while the fire paints flickering shadows on listening faces. The listener's eyes drift up to the twinkling figures above, each now alive with significance. The scientific truth of the stars, that they are distant suns, was unknown, yet perhaps the emotional truth was just as profound. That the universe was not a cold, empty void, but a storybook lit by countless points of light. As long as people have gazed upward, they have never felt truly alone, because their stories were written in the constellations. In this gentle union of imagination and sky, the night became more than darkness. It became a rich tapestry of myth and wonder that soothed the spirit. Even today, when we know the astronomy behind the stars, those old stories still cling gently to the constellations. We can step outside on a clear night and find Orion, remembering the hunter's pride and the scorpion's lesson, and perhaps smile at the thought of his faithful dog star following behind. We can spot the Pleiades and recall the sisters dancing eternally. Our modern minds know these are suns and star clusters millions of miles away, but in our hearts, they remain the magical characters and symbols our ancestors saw. The mythology of the stars continues to enrich our experience of the night. It reminds us that for all our scientific progress, we are still storytellers at heart, and the sky above remains a source of endless inspiration. As the constellations pass overhead through the year, the celestial stage brings different legends to the forefront season by season. Now, as we continue our journey, the stars that carry these myths will also guide us through the cycle of seasons, showing how the sky itself changes and tells different chapters as the Earth moves around the sun. The sky above us is not a static picture, but a grand clock, slowly turning with the seasons. As Earth makes its yearly journey around the sun, the stars we see at night change, unveiling new patterns, while others slip away until their turn comes again. Ancient people, who spent many nights under open skies, became keenly aware of this great cycle. Over the course of a year, they watched the celestial panorama shift and return, and with it came the rhythm of their lives. Imagine stepping outside on a cold winter night. The air is crisp, and your breath forms soft clouds that vanish into the dark. Above you, the constellation. Orion dominates the sky, his belt of 3 stars gleaming clear and bright. Nearby, the star Sirius, the brightest of all, sparkles like an icy blue diamond. This is the signature of winter in the northern hemisphere, a sky full of vivid, bright stars clustered together, offering a bit of cosmic splendor against the long, cold nights. Now picture yourself standing in the same spot a few months later, on a gentle spring evening. The winter figures have slipped down toward the western horizon. In their place, new stars grace the sky. Overhead, the Big Dipper has rotated to a higher perch, and a brilliant golden-orange star named Arcturus rises in the east, heralding the arrival of spring. The air carries the scent of thawing earth, perhaps the first blossoms, and frogs begin to sing in the distance. That bright star Arcturus twinkling above is like a friendly herald, reassuring everyone that winter's chill is fading and the season of renewal has arrived. When summer comes, the nights turn balmy and short. If you look up after dusk, you'll see the great swath of the Milky Way arching across the sky like a luminous river of clouds. Constellations that hid during winter now take center stage. The Scorpion, Scorpius, crawls along the southern sky, its red heart star Antares glowing like a coal of summer heat. High above, 3 bright stars, Vega, Deneb, and Altair, form the summer triangle, marking the zenith of the warmest months. The night air might be thick with the scent of flowers or the aftermath of a thunderstorm. As you gaze at the misty Milky Way overhead, you feel the fullness of summertime, the chorus of crickets and rustling leaves providing a gentle soundtrack to the starry spectacle. Then comes autumn. The evenings grow cooler and longer again. The Milky Way that dominated summer nights begins to tilt and sink, and new patterns slide into view. In the fall sky, you might find the Great Square of Pegasus, a large diamond-shaped grouping that rides high during the autumn equinox, heralding the season's change. Nearby, if you're far from city lights, you might spot a faint smudge that is actually the Andromeda Galaxy, the only galaxy beyond our own that's visible to the naked eye, though ancient skywatchers didn't know what it was. The Seven Sisters, the Pleiades cluster, sparkle on autumn nights as well, rising earlier and climbing higher as weeks go by. For many, the reappearance of the Pleiades in the evening sky was a reminder that winter was on its way once more. The cycle is coming full circle. Soon, Orion will be peaking above the eastern horizon again on chilly late autumn nights, hinting that the cold months will return. By observing such changes year after year, people long ago realized that the appearance and disappearance of certain stars were reliable markers of seasonal change. The sky became an essential calendar. Before modern clocks and schedules, nature's timing was everything, and the stars helped keep track. Each culture learned to recognize its own seasonal stars and what they signified. The ancient Greeks, for example, noted that when Orion's bright stars vanished from the evening sky, appearing only in the pre-dawn, the hot season of harvest had arrived. In one Greek poem by Hesiod, farmers are advised to begin reaping their grain when the Pleiades rise at dawn, and to finish ploughing when those stars set at dusk, using the sky as their agricultural calendar. In ancient Egypt, the first appearance of Sirius at dawn, after months of being hidden in the sun's glare, came just before the annual flooding of the Nile River. Egyptian priests would watch the eastern horizon on summer mornings with great anticipation. When that bluish star finally glinted in the dawn sky, they knew the life-giving floods were imminent, and the new year had begun. Across the ocean, the Maori people of New Zealand looked for the rising of the Pleiades in June, which they call Matariki, to mark the new year and the start of the winter season. Everywhere on Earth, at every latitude, people found that the heavens could signal when rains were due, when frosts might come, or when it was time to sow and time to reap. To ancient navigators and wanderers, seasonal stars were signposts in time as well as space. A traveller returning home after years away could look up and see the familiar constellations of his youth, knowing not only his direction but the season, and feel the comfort of home drawing near. Different stars accompany different seasons, like old friends arriving on schedule. After the long dark of winter, the return of soft spring constellations like Virgo or Leo in the evening sky promised renewal ahead. When the fiery stars of summer, Antares among them, yielded to the gentler stars of autumn, it signaled a time of harvest and preparation. The sky's storybook, which we filled with myths in every culture, also acted out a play that repeated every year, with the same characters appearing on cue, then bowing out for a while. This cyclical dance of the stars provided a deep psychological comfort. It assured our ancestors that there was order and consistency in the world. No matter how harsh the winter, they knew that when certain stars began creeping into the twilight, like the delicate glow of the Pleiades or the return of Orion at dawn, the seasons were turning and brighter days would come. Likewise, the height of summer was tempered by the knowledge that the stars of autumn would soon be rising, bringing cooler nights. Observing the heavens taught patience and an understanding that all things change in time, yet also circle back in rhythm. It's a gentle lesson. The sky may seem eternal and unchanging on any given night, but across the months it grows and matures like a living thing, then comes back to where it started. To aid in remembering and predicting these changes, early astronomers, often priests or wise elders, sometimes built structures aligned with the seasonal heavens. In England, the stones of Stonehenge are famously arranged to catch the sun's rays at the summer solstice sunrise, the longest day of the year, marking a crucial turning point in the solar calendar. Other cultures oriented temples or pyramids so that on a particular day, the light of the rising sun or a certain star would shine through a special opening or down a sacred corridor, heralding the new season or the new year. These ancient observatories, whether made of stone or earth, were calendar markers that used the sky to anchor human activities. They show just how important the celestial cycle was to farming and ritual life. Even without such monuments, the night sky itself was a trustworthy guide. One could lie on their back on a clear night and notice that each night a given star rises about 4 minutes earlier than the night before. Over weeks, those minutes accumulate into hours, and a star that rose at midnight a month ago might be rising at the start of evening a couple of months later. Ancient sky watchers knew these subtleties well. They could predict when in the year a star would first be visible at dusk or at dawn. They gave names to full moons that reflected seasonal changes, like harvest moon or hunter's moon, and they tracked the sun's slow drift against the backdrop of stars, a path we now call the ecliptic. Along that path lay the 12 constellations of the zodiac, which ancient astronomers used as reference points for the sun's annual journey. Even if they didn't fully understand why the sky changed as it did, they meticulously recorded the patterns and learned to trust them. Under the slowly shifting dome of stars, generations found guidance and meaning. The dependable cycle of the heavens likely inspired confidence that natural cycles on Earth, of weather, of growth and rest, would continue as well. Festivals and rituals were timed to celestial events, planting celebrations when certain stars rose, harvest feasts under autumn constellations, and gatherings at the winter solstice when the darkest day passed and light began to return. People felt a profound connection between the cosmic order and the human order. It's little wonder that many believed the sky's patterns and the Earth's patterns were intimately linked, each reflecting the other. For countless centuries, all this knowledge of stars and seasons, of constellations and crops, was passed down through observation and oral tradition. No telescopes or modern instruments were required, just clear eyes, careful notes, and an attentive mind. But the desire to understand the sky more deeply never faded. By the late Renaissance, human curiosity was poised to take a new leap. The cycles and movements that had been noted for ages begged for a closer look, a more detailed inspection of the cosmos that spun above. And so, as the 17th century dawned, a new tool would be turned toward the heavens. This device, the telescope, would reveal wonders and truths that early stargazers could scarcely have imagined. With it, the night sky's timeless cycle would remain. But our view of the universe and our place within it was about to expand dramatically. In the early 17th century, after millennia of gazing at the sky with just human eyes, a dramatic new window to the cosmos opened. Imagine a still evening in 1609 in Padua, Italy. A scholar named Galileo Galilei carries a curious instrument up to the rooftop of his home. It looks like a long, narrow tube made of wood and leather. Galileo has heard rumours that in distant Holland someone has crafted a device that makes far-off things appear closer. With his own hands, he has built something similar, placing carefully shaped glass lenses at each end. Now, as darkness falls, he lifts this contraption, a telescope, toward the night sky for the very first time. At first, Galileo points his telescope at the moon. Through the eyepiece, the familiar bright disk suddenly reveals an astonishing sight. The moon's surface is not the smooth, perfect orb that philosophers had imagined, but a rugged landscape of mountains and craters. He sees shadows pooling in lunar craters and bright rims of peaks catching the sunlight along the moon's day-night boundary. The moon, which for ages was thought to be a flawless heavenly sphere, appears startlingly like a world with geography, more like Earth than anyone had guessed. Galileo's heart pounds with excitement. What else might this new tool reveal? He turns the telescope toward the planet Jupiter, which to the naked eye is just another bright star. In the telescope's view, Jupiter becomes a small but clear disk, and something more. Dotted around it are 4 tiny points of light, lined up like a miniature solar system. Night after night, Galileo observes these little stars near Jupiter and notes how they change position. Sometimes 1 or 2 vanish, eclipsed by Jupiter's glare, and reappear later. He soon realizes these are not stars at all, but moons circling Jupiter. This discovery shatters the old idea that everything in the heavens must revolve around Earth. Here is direct evidence that another planet has satellites of its own. One can only imagine Galileo's astonishment at this realization. With a simple tube and 2 pieces of glass, he has expanded the known universe. The Earth is not the sole center of motion. There are other centers, other worlds in orbit out there. Eagerly, Galileo charts more wonders. He observes that Venus shows phases like the moon, from slender crescent to half-lit to full, which only makes sense if Venus orbits the Sun, shining from different angles. He directs his telescope to Saturn and is perplexed. The planet isn't a single round globe, but seems to have odd appendages on either side, almost like handles. His telescope isn't powerful enough to reveal the rings clearly, so he sketches Saturn as a planet with ears. He aims at the Milky Way, that milky band across the sky, and what he sees forever changes our understanding of it. The soft, pale glow dissolves into countless faint stars. The Milky Way is not a cloud or a celestial river at all, but a multitude of distant stars packed together. The night sky that once offered only a few thousand visible stars suddenly contains vastly more, an ocean of stars stretching into depths previously unimagined. News of these discoveries spreads across learned circles in Europe. Some greet it with excitement and curiosity, others with disbelief or even alarm. But the telescope's revelations cannot be hidden. Other astronomers point their own homemade telescopes upward and confirm Galileo's findings. In England, observers like Thomas Harriot marvel at the rugged moon through their lenses and draw some of the first crude lunar maps. In Prague, Johannes Kepler, though his weak eyesight keeps him from observing much himself, pores over Galileo's reports and uses them to refine the laws of planetary motion. The sky, once constant and perfect in theory, is revealed as dynamic and populated with objects both strange and familiar. Over the next decades and centuries, telescopes grow in size and power. In 1655, Dutch astronomer Christian Huygens, using a better telescope, discerns that Saturn's ears are actually a broad, thin ring encircling the planet, separate from the planet itself. He also discovers a large moon orbiting Saturn, later named Titan, adding to the list of moons that Galileo began. In 1781, Sir William Herschel, peering through a telescope from his garden in England, notices a tiny blue-green disk that turns out to be Uranus, the first new planet discovered in recorded history. The more people looked, the more the cosmos opened up. What once were indistinct smudges in the night sky, nebulous patches that people thought might be clouds or simply unknown stars, were resolved by larger telescopes into star clusters and glowing nebulae. Each improvement in our instruments brought new wonders into focus. For those alive in those early years of telescopic discovery, it must have felt like an age of miracles. Humanity had acquired a new sense, a kind of supervision that could leap across space. With it, the moon became a landscape to explore, the planets became places to ponder, and the stars themselves multiplied into uncountable numbers. Ideas that had been abstract speculation were now visible realities. The Polish astronomer Copernicus, who decades before had proposed that Earth moves around the Sun, was vindicated by Galileo's observation of Venus's phases. Our conception of the universe rapidly evolved from a tidy, Earth-centered arrangement into something far more vast and intricate. Yet for all these groundbreaking revelations, there was also profound beauty in what the telescope revealed. Early astronomers often wrote not just about the science, but about the splendor of their sights. The jewel-like appearance of Jupiter, with its retinue of moons, the serene glimmer of Saturn's rings, or the silvery mist of star clusters turning to diamonds against a black backdrop. Imagine the sense of wonder Galileo must have felt looking at the Pleiades cluster under magnification. Dozens of dim stars suddenly popping into view, ones invisible to his unaided eye, as if the little cluster had blossomed with new points of light. Or the feeling of discovery when peering at the Orion Nebula, first noted just a few years after Galileo, by astronomers using his invention. A faint fuzzy patch in Orion's sword that, under the telescope, revealed itself as a gauzy, glowing cloud studded with newborn stars. The universe was not only larger than we thought, but more varied and beautiful, filled with structures and phenomena we had never even imagined. Of course, the telescope was only the beginning of a new era. Galileo's first instrument was tiny and simple by today's standards. It magnified about 20 times, and its views were blurry at the edges. But it was enough to spark a revolution. In the years and centuries that followed, craftsmen and scientists built ever better telescopes. First longer refracting telescopes with bigger lenses, then reflecting telescopes with mirrors. An innovation introduced by Isaac Newton to eliminate the rainbow distortions that simple lenses produced. With each leap in capability, we peered a little farther. We observed the moon in greater detail, seeing its craggy mountains and wide lunar seas. We followed the wandering spots on the sun to learn that our own star rotates. By the 19th century, telescopes had revealed new classes of objects: tiny moons around Mars, a belt of asteroids between Mars and Jupiter, and mysterious oval and spiral nebulae out in deep space, hints of galaxies beyond our own, though we wouldn't understand their true nature until much later. But let's not race too far ahead of our story. In Galileo's time, even the idea of what stars truly were remained a mystery. His telescope showed that they were far more distant than anyone had guessed, since through his telescope they remained mere points of light, not disks like planets. He correctly inferred they must be immensely far away. This realization pushed the boundaries of the known cosmos outward dramatically. The comfortable, finite crystal spheres that medieval scholars imagined were now shattered. In their place was an open, perhaps infinite expanse filled with stars and wonder. One can picture Galileo and his contemporaries standing in the chilly night air, eye pressed to their new devices, gasping softly at sights no human had ever seen before. The night would have been silent, save perhaps the distant chirp of an insect or the rustle of a breeze, and the quiet exclamations of excitement from these first observers. The universe felt closer, and yet more mysterious than ever. Each discovery solved one riddle, but presented new questions. If the moon has mountains, might it not be a world of its own? If Jupiter has moons, could those moons themselves have smaller moons or secrets? What exactly were Saturn's rings made of? How far away were the myriad faint stars that now speckled Galileo's view? The telescope opened the door to countless questions that would occupy scientists for generations to come. And so, with the first telescopes, the era of modern astronomy was born. Humanity's childlike wonder at the stars was now combined with a new ability to scrutinize them. The sky was no longer just a pretty backdrop for myths or a clock for marking seasons. It was a place we could examine, a place full of dynamic worlds and phenomena. The legacy of those early observers is immense. They taught us that by extending our senses, we could deepen our understanding without diminishing the enchantment of the universe. In fact, the more we saw and learned, the more our sense of wonder grew. As this chapter of stargazing history draws to a close, imagine Galileo carefully setting aside his telescope after a long night's vigil. The eastern sky begins to pale with approaching dawn, and one by one, the stars he has been observing fade into the morning light. He rubs his tired eyes, filled not with exhaustion, but with fulfillment. He has seen things few others on earth have ever seen. The universe has opened itself to him just a little, sharing some of its secrets. In that still, pale, early morning air, perhaps Galileo allows himself a small, satisfied smile, knowing that this was only the beginning. The telescope had shown what was possible. There were endless mysteries still out there, waiting for curious eyes and better tools. The silent stars, which had inspired wonder since the dawn of humanity, were at last starting to speak to us in a new language of light and discovery. Galileo and his contemporaries could scarcely imagine how far that journey would go. But we know that the story continues, from those first modest spyglasses to the sophisticated observatories and space telescopes of our era. Each generation builds on the last, always pushing further into the vast cosmic ocean. Yet even now, if you step outside on a clear night and look up, you can feel a kinship with Galileo's sense of wonder. The stars still sparkle with the same gentle light. They invite us to keep exploring, keep learning, and keep marveling. The more we uncover about them, the more profound and beautiful the night sky becomes. We carry forward both the wisdom of those who came before and the curiosity that will guide those who follow into the unknown, ever onward, beneath the stellar mysteries and galactic wonders above. For countless generations, people gazed at the night sky and imagined the stars as eternal beacons, unchanging, everlasting lights sprinkled across the darkness. It was long believed that these brilliant points were fixed in the heavens, constant and perpetual. But in truth, stars have their own secret lives. They are born out of darkness. They shine with youthful vigor. They age and transform. And ultimately, each in its time, they perish. And so, our journey now turns to the life story of the stars themselves, beginning where every star's tale begins, in the mysterious nurseries of the cosmos. In the cold expanse of a galaxy, vast clouds of gas and dust drift in silence. These are nebulae, the stellar nurseries where new stars are born. To the eye they appear as faintly glowing patches, or sometimes as dark silhouettes blocking the starlight beyond. They are beautiful, ethereal clouds, often stretching across dozens of light years. Within them, deep in their densest regions, something quietly profound is happening. Under the gentle but persistent pull of gravity, the gas and dust begin to gather into clumps, each clump destined to become a new star. What causes a particular patch of cloud to collapse into stars? Often, it's a gentle nudge or shock from outside, a passing shock wave from a distant supernova explosion, or the gravitational disturbance from a nearby star, or the passing spiral arm of a galaxy can squeeze portions of a nebula. Once a region becomes dense enough, gravity takes charge, and the collapse accelerates. In this way, one generation of stars can trigger the birth of the next, a kind of cosmic handoff of the torch. The process is usually slow and hidden, but dramatic events can hasten it. For instance, when massive stars at a nebula's edge erupt as supernovae, their shockwaves compress the remaining gas, sowing the seeds for new stars in a cascading cycle of star birth and death. Inside each contracting clump, gravity's relentless squeeze raises the temperature and pressure. The heart of the clump begins to glow faintly, not yet with starlight, but with heat. This is a protostar, a newborn star still wrapped in its natal cocoon, not yet hot enough for true fusion fire. The protostar continues to gather mass, drawing material from the surrounding cloud. As it does, it starts to spin, and a flattened disk of gas and dust forms around it. In that swirling disk, tiny grains may one day coalesce into planets, moons, and asteroids. For now, all is still shrouded in darkness and dust around the protostar. It grows denser and hotter over tens of thousands, even millions of years. And then, at last, comes the moment of first light, when the core becomes hot enough to ignite nuclear fusion. At that instant, a star is born, and it begins to shine. Young protostars often announce themselves not only by heat, but by motion. As material spirals in through the accretion disk, some of it gets channeled along the star's magnetic poles and blasted back out into space. The result is a pair of narrow jets shooting in opposite directions from the protostar. These jets plough through the surrounding nebula at high speeds, creating glowing shock fronts where they slam into the gas. Astronomers spot these as peculiar streaks or knots of nebulosity, known as Herbig-Haro objects. They are like neon signposts, marking the presence of a forming star buried in its dusty nursery. In time, when the star fully ignites, these jets may fade, but while they last, they help clear away excess gas and announce the star's birth with a flourish of motion and energy. With fusion ignited, a newborn star truly begins to shine. Its radiation and stellar winds blow outward, pushing back against the surrounding nebula. The once hidden star starts to emerge from its dusty cradle, often carving out a bubble or cavity in the cloud. Sometimes we see dramatic shapes left behind, great cavities and pillars sculpted in the nebula by those intense starlight and winds. In the famous Eagle Nebula, for example, towering columns of gas known as the pillars of creation are being eroded by the brilliant young stars forming within them. As the gas clears, the newborn stars step into view, sprinkling the darkness with new light. One of the most famous stellar nurseries is the Orion Nebula, visible as a faint patch in the sword of the constellation Orion. To the unaided eye, it seems like a modest blur, but through a telescope, it blossoms into a magnificent bay of glowing gas and newborn stars. The Orion Nebula lies about 1/300 light-years away, a cavern carved out in a giant molecular cloud where thousands of stars are taking shape. At its heart, a cluster of massive young stars, known as the trapezium, blazes brightly. Their intense ultraviolet radiation causes the surrounding gas to glow in hues of pink and green, illuminating the nebula like a cosmic grotto. Throughout the Orion Nebula, dark filaments and curtains of dust snake across the glowing backdrop. These dense streaks are the birth cocoons for new stars. Within them, embryonic protostars are still gathering mass, hidden from direct view. Only infrared telescopes can peer into those dusty wombs to reveal the faint warmth of the forming stars inside. The entire scene is one of dynamic creation, a tempest of star birth frozen in a moment of time. Nebulae like Orion are sprinkled all over our galaxy, especially along its spiral arms. Each marks a place where the galaxy is actively forging new suns, ensuring that the stellar cycle continues onward. Newborn stars are often not alone. They are born in communities. A single giant cloud can give birth to hundreds or thousands of stars at once, like a cosmic brood. These sibling stars may form loose clusters, bound together in their youth by gravity. They drift together through the galaxy for millions of years, until time and tidal forces disperse them. Our own sun was likely born in such a cluster, alongside many sister stars. Though those siblings have long since wandered elsewhere in the Milky Way, the sun carries their shared origin story, one star among many that sparkled to life in the same nursery. The night sky offers a glimpse of such stellar siblings in the Pleiades star cluster. The Pleiades, the seven sisters of Law, are a group of young blue-white stars in the constellation Taurus that were born together about 100 million years ago. They are still gathered in a tight cluster, and on a dark night, one can see their tiny dipper-like formation. A faint, hazy glow around them, visible in long-exposure photographs, is a delicate veil of dust reflecting their starlight, possibly a remnant of the nebula that gave them birth. Though the Pleiades are relatively close-knit now, they will not remain so forever. Over hundreds of millions of years, the cluster's stars will gradually drift apart. Gravitational interactions with other passing stars and clouds in the galaxy will tug at the siblings until they disperse. This fate is common for open star clusters. Our Sun's own birth cluster likely dissolved in this way eons ago, its members now scattered and mingled among the Milky Way's other stars. But for a time in their youth, clusters like the Pleiades are cosmic families, groups of stars travelling together through space, shining side by side before the tides of the galaxy separate them. These stellar nurseries are rich not only in hydrogen gas, but also in the recycled material of earlier stars. Within the nebula's dust are atoms of carbon, oxygen, iron, and other elements that were forged in the hearts of older stars and spread through space by ancient supernovae. When a new star forms, it inherits this cosmic ash of previous generations. Around those new suns, some of that material can gather into planets, moons, and all the ingredients for life. In this way, each star's birth is not just a beginning, but also a continuation, a link in the eternal chain of cosmic evolution, carrying the echoes of stars that lived and died long before. Through patient eons, the dark gives way to light. What was once a cold, diffuse cloud becomes a hot, shining star. In modern times, with powerful telescopes, we can peer into these nebulae and witness stars in the making, infant suns still swaddled in glowing gas. Every star in the sky, including our sun, began in such a nursery. Now, having emerged from their birth clouds, these stars will spend the vast majority of their lives steadily burning. But how do they sustain that radiance for so long? What powers a star's shining heart and keeps it glowing through the ages? Deep within each star lies its power source, an unimaginably hot and dense core where the real magic happens. Temperatures of many millions of degrees and intense pressures crush atoms together. Under these extreme conditions, hydrogen nuclei, protons, fuse to become helium. In the process, a tiny bit of mass is converted into a tremendous amount of energy. This is the secret of starlight, nuclear fusion. Every second, in a star's core, countless fusion reactions release bursts of energy that begin to work their way outward. It is this energy, born in the core, that eventually reaches the surface and shines into space as the light and warmth of the star. Along with light, the fusion in the core produces ghostly particles called neutrinos. Unlike photons, neutrinos hardly interact with matter and escape the star almost instantly. Every second, trillions of them stream out from the sun's core and pass through Earth, and even through our bodies, without a trace. Deep in underground laboratories, scientists have built detectors that catch a tiny fraction of these neutrinos. By observing them, we've gained direct confirmation of the sun's core reactions. It's awe-inspiring to realize that particles born at the sun's center arrive here on Earth just minutes later, providing a fleeting glimpse into the sun's hidden heart. The energy rushing outward from fusion creates an outward pressure, like the push of hot gas desperately wanting to expand. This push fights against the inward pull of the star's own gravity. In a stable star, these two forces balance perfectly. Gravity tries to collapse the star, but the pressure from the hot, glowing core pushes back and prevents the collapse. The result is a long-lasting equilibrium, a harmonious tension that allows the star to burn steadily for a very long time. This is how a star sustains itself, a constant tug-of-war between gravity and internal fire, with neither side winning for eons. Consider our Sun, a rather ordinary star. In its core, about 4 million tons of matter are converted into energy every second. This sounds almost unbelievable, yet the Sun is so massive that it can keep doing this for billions of years. It has already shone for about 4.6 billion years, and it's roughly halfway through its prime of life. The light we see from the Sun today was generated in its core long ago and took a long, wandering journey to reach the surface. A photon created at the Sun's center may bounce around inside for tens of thousands of years before finally escaping into space. Once free, that light takes only about 8 minutes to travel across the 150 million kilometers to Earth. In a sense, the sunshine we feel on our faces is ancient energy, forged in a stellar furnace and then released to wander the cosmos. Not all stars burn their fuel at the same rate. The mass of a star is like a cosmic throttle, determining how quickly the star lives its life. A very massive star cranks out energy at a furious pace. It may shine tens of thousands of times brighter than a small star. But that brilliance comes at a cost. The star consumes its fuel voraciously and thus lives a relatively short life. A giant blue-white star might burn through its core hydrogen in only a few million years, blazing intensely until it has nothing left to fuel its fire. By contrast, a small red dwarf star, with far less mass and a much gentler glow, sips at its fuel slowly. These diminutive stars are dim, but they endure for an incredibly long time. A red dwarf can shine not for millions, but for tens of billions, even trillions of years. In fact, the universe itself isn't old enough for any of these tiny stars to have burned out yet. While the big stars live fast and perish young, the little red stars live slowly and seem almost timeless from our perspective. In essence, a massive star is like a gas-guzzling sports car engine, running hot and bright, but racing through its fuel quickly. A small red dwarf is like a slow-burning oil lamp, conserving fuel and glowing gently for ages. The Sun, by comparison, is more like a reliable family sedan, moderate in its fuel consumption, destined for a long, stable ride. These differences mean that the stellar population of a galaxy is skewed towards long-lived small stars. For every short-lived giant that flares brilliantly and dies, there are countless red dwarfs quietly glowing for eons. If one could look at the Milky Way in infrared light, which highlights cooler objects, one would see it dominated by the soft red glow of these abundant little stars that far outlive their more flamboyant massive cousins. For a star on the main sequence, as astronomers call this long, stable burning phase of a star's life, things are relatively steady. Our Sun has been in this phase for billions of years. Barring minor cycles like the Sun's 11-year sunspot oscillation, which changes its energy output by only a fraction of a percent, the Sun's brightness and heat have remained remarkably constant through human history. This stability is precisely why life has been able to flourish on Earth. Our Sun's energy arrives reliably, day after day, without violent fluctuations. Main sequence stars are true beacons of steadiness in the cosmos. Eventually, however, even this comfortable phase must end. When a star begins to run out of its core fuel, its outward appearance and behavior will change, preparing us for the later acts of a stellar life. For eons, a star in this stable stage quietly converts hydrogen to helium, turning mass into light. This is the main act of a star's life, and during this time, the star appears essentially unchanging to us. Our night sky is filled with stars in this long, steady midlife stage, each a beacon fueled by its core fire. Yet even though they all shine from the same fundamental process, stars do not all look the same. Some glow blue-white and fierce, others golden or red and mild. The colour of a star's light is a clue to its temperature and character, a signature of the fire that burns within. By observing the colours and subtle details of starlight, we can begin to decipher what each star is like on the inside. Look up at the stars on a clear night, and you may notice they are not all the same colour. Some shimmer with a bluish-white tinge, others appear golden, and some flicker with a faint orange-red warmth. This colour is not an illusion, it's a direct result of their surface temperature. Just as an iron rod glows dull red when heated and turns white hot at even higher temperatures, a star's hue tells us how hot its surface is. Hotter stars emit more blue and ultraviolet light, making them appear blue-white to our eyes. Cooler stars emit more red and infrared light, giving them a gentle reddish or orange glow. Thus, the colour of a star is like a cosmic thermometer in the sky. Blue means blisteringly hot, while red means comparatively cooler, though still thousands of degrees. In the constellation Orion, one can easily see this contrast. Rigel, one of Orion's brightest stars, shines with an icy blue-white light, an indicator of its searing surface temperature, on the order of 20,000 degrees. Meanwhile, at the opposite shoulder of Orion, Betelgeuse smoulders with a dull red-orange hue. Betelgeuse is much cooler, only a few thousand degrees at its surface, and it is a gigantic star nearing the end of its life. The stark difference in colour between Rigel and Betelgeuse reflects just how diverse stars can be. Each star's light carries a fingerprint of its temperature, and often its size and stage of life as well. Our Sun is a yellow-white star, with a surface temperature of about 5,800 degrees Celsius, around 10,000 degrees. In space, the Sun actually shines a pure white. Our atmosphere makes it look yellowish to our eyes at noon, a typical colour for a mid-temperature star. Many of the stars we see twinkling at night are hotter and more luminous than the Sun. That's why they stand out from dozens or even hundreds of light years away. Meanwhile, the most common stars in our galaxy are actually the cool red dwarfs, which are so faint we can't see any of them without a telescope. These little crimson stars, making up the majority of all stars by number, hide in plain sight due to their low brightness. So the stars we easily notice in the sky are a special set, often either very hot, very large, or relatively nearby. The vast backdrop of dim red dwarfs remains invisible to our unaided eyes, quietly making up the bulk of the Milky Way's stellar population. Astronomers classify stars into spectral types labelled O, B, A, F, G, K, and M, a sequence from the hottest to the coolest. O-type stars are extremely rare and massive, with surface temperatures of tens of thousands of degrees, shining a fierce blue-white. M-type stars are very common red dwarfs, relatively cool and faint, but incredibly numerous. Our Sun is a G-type star, on the warmer side of middle in this scheme. Each spectral class has a unique pattern of spectral lines. For instance, cool K and M stars show molecular bands in their spectra, whereas hot O stars exhibit lines of ionized helium. By matching a star's spectral fingerprints to these classes, astronomers can gauge its temperature and general nature from light years away, yet another wealth of information carried by starlight. By analysing thousands of stars, astronomers found that colour and brightness are linked in a grand pattern. If we plot stars on a graph with their surface temperature, or color, on one axis, and their intrinsic luminosity, true brightness, on the other, a remarkable sequence emerges. Hot, blue stars of high luminosity lie at one end, and cool, red, faint stars lie at the opposite end, with stars of intermediate colors and brightness filling in between. This continuous band of points is called the Hertzsprung-Russell diagram, or HR diagram, and it reveals an underlying order in stellar properties. Along the main diagonal of the HR diagram lies the main sequence, where stars spend most of their active lives steadily fusing hydrogen. Our Sun sits on this band, a mild G-type star of moderate temperature and brightness. Above this band are the red giants and supergiants, stars cooler in surface temperature but tremendously bright, which means they must be enormous in size. Below the main sequence are the white dwarfs, stars that are very hot yet dim, indicating they are tiny. Simply by locating a star on this chart, one can discern whether it is a sun-like star in midlife, a bloated giant nearing its end, or a shrunken dwarf left in a star's afterlife. The HR diagram is a fundamental tool in astronomy, effectively a map of stellar evolution gleaned from the clues of color and light. There is far more information in starlight than just its color. If we take a star's light and pass it through a prism or a spectroscope, it spreads out into a rainbow of colors. Its spectrum. Embedded in that spectrum are subtle dark lines at particular colors, like a secret code. These lines are caused by elements in the star's outer layers absorbing specific wavelengths of light. By studying these absorption lines, astronomers can tell what a star is made of without ever touching it. We can identify hydrogen, helium, calcium, iron, and many other elements present in the star, all through careful analysis of its light. This technique, called spectroscopy, has revealed remarkable things. We learned that stars, including our Sun, are composed mostly of hydrogen, with helium as the second most abundant element. In fact, helium was discovered on the Sun before it was found on Earth. Its telltale spectral line was observed during a solar eclipse in 1868, tipping off scientists to an unknown element, later named helium after Helios, the Greek sun god. A star's spectrum can even divulge its motion. Tiny shifts in the positions of the spectral lines, caused by the Doppler effect, reveal whether a star is moving toward us or away from us. It's similar to how a siren's pitch changes as an ambulance passes by. By measuring these shifts, we can determine if a star is wobbling, perhaps due to orbiting a companion, or speeding through space. In essence, a star's light is a rich and nuanced signal, carrying the story of its physical properties across the vastness of space. Beyond the visible spectrum, stars shine in forms of light our eyes cannot see. Ultraviolet and X-ray observations, for example, reveal the fierce high-energy output from the hottest young stars, and from explosive activity like flares on stars, while infrared observations can unveil the gentle warmth of cooler stars that are otherwise too dim to notice. Even objects like brown dwarfs, failed stars, not massive enough to sustain fusion, glow primarily in infrared and would be almost invisible without it. By collecting all these different kinds of light, astronomers form a much more complete picture of a star. Each wavelength, from radio waves to ultraviolet to X-rays, brings out different details, revealing various layers and processes in and around the star. A star that is dim and almost invisible to our eyes might be brilliant in infrared or radio. Modern astronomy extends human vision into these realms, allowing us to truly see the full spectrum of a star's light and glean every secret the star is willing to share. By studying the color and spectrum of a star's light, we can uncover an astonishing amount of knowledge. How hot the star is, what it's made of, how large it might be, and even how it's moving through space. Light is the language of the stars, and over time we have learned to read it well. In fact, it is remarkable that without ever visiting a star, we can infer so much about it just by analysing the faint glow that reaches our telescopes. To our eyes, most stars appear to shine with a steady, unwavering light, each with its own characteristic colour and brightness. Yet not all stars are constant beacons. Some behave almost like living, breathing creatures, their light waxing and waning over time. Instead of a permanently steady glow, these variable stars brighten and dim in cycles or sudden spurts. To people of antiquity, such changes in the heavens were startling and mysterious. Today, we understand many of the reasons why a star might vary in brightness, but that knowledge hasn't diminished the wonder. A star that rhythmically pulsates or suddenly erupts is among the most captivating phenomena in the cosmos. Now, let us explore these celestial heartbeat rhythms, the stars that change their light as if alive, the true beating hearts of the galaxy. Stars that change their brightness intrigued and mystified sky watchers for centuries. One of the first known was a star in the constellation Cetus that would appear, disappear, and reappear over months. In 1596, the Dutch astronomer David Fabricius noted its curious behaviour, and later astronomers named it Mira, the Wonderful, for its strange, marvellous nature. We now know Mira is a pulsating red giant star, swelling and contracting in a cycle that lasts about 11 months, causing its brightness to swing dramatically. Mira was the first of many variable stars documented, each with its own pattern and reason for changing brightness. It became clear that not all stars shine with a steady light. Some are alive with periodic beats or sudden flares, like hearts that pulse or fireflies that flicker in the night. Many variable stars are pulsating variables, meaning the star rhythmically expands and contracts, which changes its brightness. Imagine a star breathing in and out. When the star's outer layers compress, the star gets hotter and brighter. When those layers expand outward, they cool slightly and the star grows dimmer. This cycle can repeat very regularly. Deep inside the star, a delicate imbalance causes these pulsations. Typically, layers of ionized gas act like a valve, trapping heat until pressure builds and forces the star to expand, then releasing and letting the star contract again. The result is an oscillation, a steady throb of light. To an observer, the star appears to brighten and fade, as if it truly has a heartbeat. Among the most famous pulsating stars are the Cepheid variables. These are giant stars, several times more massive than the Sun, that pulsate in a very regular way. A Cepheid will steadily brighten, reach a peak, then dim again over a period that can range from a few days to a couple of months, and this cycle repeats like clockwork. Crucially, there is a pattern. The longer the period of pulsation, the more luminous the Cepheid intrinsically is. In other words, a Cepheid that takes, say, 30 days to complete a cycle is far brighter in reality than one that takes only 5 days. This relationship between period and luminosity was discovered in 1908 by astronomer Henrietta Swan Leavitt. It turned out to be a tremendously important cosmic tool. Using Leavitt's discovery, astronomers realized that by measuring how long a Cepheid takes to vary, they could determine its true luminosity. By comparing that true brightness to how bright it appears from Earth, one can figure out its distance. Much like knowing a candle's actual light output, and seeing how faint it looks tells you how far away it is. In the 1920s, Edwin Hubble observed Cepheid variables in the Great Andromeda Nebula and used this method. He found that Andromeda was far, far beyond the bounds of our Milky Way, revealing it to be an entire separate galaxy. Cepheid variable stars thus became beacons that expanded our understanding of the universe. They are literally yardsticks for the cosmos, their gentle blinking helping us measure the vast distances across space. Cepheids are not the only pulsating variables. There are also RR Lyrae stars, which are smaller and older stars that pulsate with shorter periods, typically less than a day. They follow a similar principle: regular cycles of brightness tied to intrinsic power. RR Lyrae variables are found in globular clusters and in the halo of our galaxy, and they too serve as distance indicators, though for shorter ranges than Cepheids. Thanks to these stars, astronomers can gauge distances within our Milky Way and to nearby clusters with great accuracy, filling in another rung of the cosmic distance ladder. Not all variable stars pulsate. Some vary because of celestial geometry. Eclipsing binary systems are a prime example. Two stars orbit each other, and if aligned just right with our line of sight, one star will periodically eclipse the other. When the fainter star passes in front of the brighter star, the total light we see from the pair drops for a time, even though neither star's intrinsic luminosity has changed. After the eclipse, the light returns to normal. This creates a cyclic dimming and brightening pattern. A classic case is Algol in the constellation Perseus. Algol's brightness visibly fades and then brightens every 2.87 days, like clockwork. For a long time, it puzzled observers and earned Algol the nickname the Demon Star in ancient lore, as if a sinister force were causing it to wink. Today we know Algol is an eclipsing binary. A dimmer companion star regularly passes in front of a brighter primary star, and each orbit brings a brief dip in light, an eclipse, that causes Algol's observed brightness to drop. What seemed eerie and inexplicable to the ancients is now recognized as a predictable celestial dance. Two stars taking turns eclipsing one another in a cosmic waltz. Other stars are irregularly variable, experiencing sudden flares or outbursts. For instance, some young red dwarf stars can unleash powerful stellar flares, causing a brief spike in brightness as their magnetic fields snap and reconnect, a much more dramatic version of our sun's solar flares. And in certain close binary systems, a white dwarf star can siphon gas from a companion and undergo a burst of fusion on its surface, an event called a nova, which can make the star system suddenly brighten by a large factor and then slowly fade again. These more erratic variables remind us that stars are dynamic objects capable of surprises. Although their causes differ, pulsation, eclipse, eruption, all variable stars add a fascinating dynamism to the cosmos. They are the universe's way of showing that even stars have cycles, rhythms, and moments of dramatic change. By observing variable stars, we witness stars in flux, not motion through space, but changes in their very nature. Some of these changes are the prelude to a star's later life stages. A pulsating red giant like Mira, for example, is nearing the end of its life and is gently shedding its outer layers with each beat, preparing to cast off its atmosphere. Eventually, many variable stars will undergo far more dramatic transformations once their fuel is exhausted or their delicate balances break down. To understand how a star's story concludes, we must explore the fates that await them when their shining youth and stable midlife come to an end. The final chapters of stellar life are as diverse as the stars themselves. Let us now witness the many ends a star can meet, from the tranquil fading of a white dwarf to the spectacular death throes of a supernova. stars like our Sun will end their lives in a relatively gentle manner. After billions of years of steadily burning hydrogen, a Sun-like star eventually exhausts the fuel in its core. When that time comes, for our Sun, roughly 5 billion years from now, the core will contract and heat up, while the outer layers puff outward. The star swells into a red giant, a huge cooler star dozens of times its original size. In the Sun's case, it will expand so much that it may engulf Mercury, Venus, and perhaps even Earth. During the red giant phase, new fusion reactions can ignite in the star's interior, for instance, helium fusing into carbon. This provides a temporary reprieve, allowing the star to shine a while longer. But eventually, those fuels are exhausted as well. Unable to sustain its full brilliance, the star begins to gently shed its outer layers into space, creating an expanding, glowing shell of gas around it. Astronomers call this shell a planetary nebula. Not because it has anything to do with planets, but because in early telescopes, these round gas clouds resembled planetary disks. These planetary nebulae often appear strikingly beautiful when seen through telescopes or in photographs. They can take on ring-like or bubble-like shapes, glowing in vivid colours, a green or turquoise hue from oxygen gas, and reddish tones from hydrogen and nitrogen. The Ring Nebula in Lyra, for example, is a glowing smoke ring in the sky, and the Helix Nebula in Aquarius looks like a giant cosmic eye. Such nebulae reveal complex patterns of shells and filaments in the ejected gas. Each one is like a delicate cosmic artwork, marking where a star gently released its outer layers to space. At the center of the nebula lies the former core of the star, now exposed and fiercely hot. With fusion extinguished, this core becomes a white dwarf, a tiny, dense, stellar ember about the size of Earth, glowing with leftover heat. Over billions of years, the white dwarf will cool and fade, eventually becoming a cold, dark remnant, sometimes called a black dwarf, though the universe isn't old enough for any to exist yet. A white dwarf is normally an end state, the final cinder of a star that was once like the Sun, slowly cooling in the dark. However, if that white dwarf has a close companion star, the story can take an unexpected turn. The dwarf may steal gas from its neighbour, siphoning matter onto its surface. If enough material piles up, pushing the dwarf over a critical mass limit, it triggers a runaway thermonuclear explosion. In an instant, the entire white dwarf is blown apart in what's called a Type Ia supernova. This explosion is so bright, it can outshine a whole galaxy for a short time. Unlike the core collapse supernova of a massive star, which leaves behind a neutron star or black hole, a Type Ia supernova leaves no stellar remnant at all. The white dwarf is completely obliterated. What remains is a huge expanding cloud of debris, rich in heavy elements. These supernovae are one of the primary ways elements like iron are spread into the cosmos. They also have another importance. Because Type Ia supernovae explode with near uniform brightness, astronomers use them as standard candles to measure distances across the universe. By observing how bright such a supernova appears from Earth, we can gauge how far away its host galaxy is. In this way, even in destruction, these dead stars help illuminate and map the cosmos. For stars far more massive than the Sun, the ending is spectacularly violent. A high-mass star, perhaps 10 or more times the Sun's mass, lives fast and dies young, burning through its nuclear fuel in only a few million years. When its core fuel is finally exhausted, the star faces catastrophe. No longer supported by the pressure of fusion, the iron core, the final ash of the star's fusion processes, succumbs to gravity and collapses in an instant. The core implodes, and the sudden collapse triggers a colossal rebound, a shock wave that rips outward through the star. The star explodes as a core collapse supernova, one of the most powerful explosions in the universe. In the aftermath, the star's brightness surges to unimaginable levels. For a short time, it can outshine all the billions of other stars in its galaxy combined. The explosion hurls the star's outer layers into space at tremendous speed. Glowing debris races outward, creating a supernova remnant, an expanding shell of hot gas and dust that will continue to spread into the surrounding space for thousands of years. Astronomers are watching certain massive stars in our galaxy that could be future supernovae. One famous example is Betelgeuse, the red supergiant marking Orion's shoulder. Betelgeuse is in a late stage of its life and is expected to explode as a supernova sometime in the next few tens of millennia, a mere eye blink in cosmic terms. When it does, it could blaze as brightly as the moon in Earth's sky for weeks, visible even in daytime. Such a nearby supernova would be a breathtaking spectacle, and at around 600 light-years distance, fortunately not harmful to us. Historical records tell of supernovae witnessed by humans. For example, in the year 1054, a supernova was observed that later left behind the Crab Nebula. When Betelgeuse's time comes, future skywatchers will have a front-row seat to a star's spectacular finale. Such supernovae, though destructive, are also creative. In the ferocious heat and pressure of the blast, new heavy elements are forged. Gold, silver, iodine, uranium, and many more that the star could not produce during its life. Those newly made atoms are hurled far and wide into interstellar space, seeding the galaxy with enriched material. In time, they will mix into giant gas clouds and become part of new stars, new planets, and perhaps new living beings. In fact, the iron in your blood and the calcium in your bones were forged in a star that died long before the sun was born, its ashes cast across space by a supernova. Truly, we are made of star stuff, the legacy of stars that lived and died, contributing their substance to the universe's ongoing story. What remains of a massive star after a supernova depends on how much of the core survives. In many cases, the collapsed core endures as an exotic object called a neutron star. If you can imagine, a neutron star packs more mass than the Sun into a sphere only about 20 kilometers, 12 miles, across. It is essentially a giant atomic nucleus, matter crushed so tightly that electrons and protons merge into neutrons. A teaspoon of neutron star material would outweigh a mountain. The gravity on its surface is unfathomably strong. If you stood on a neutron star, an impossibility of course, you would weigh billions of times what you do on Earth, and you'd be instantly flattened by the gravity. Neutron stars also tend to spin rapidly. They are born small and compact, and like a twirling ice skater pulling in her arms, they rotate faster as they shrink. A fresh neutron star can rotate dozens or even hundreds of times per second. Neutron stars often possess extremely strong magnetic fields as well. They can emit intense beams of electromagnetic radiation, radio waves, light, even X-rays, from their magnetic poles. As the star spins, these beams sweep around like lighthouse beacons. If one of those beams periodically points toward Earth, we detect a pulse of radiation with each rotation. This is what we observe as a pulsar. A famous example lies in the Crab Nebula, the expanding debris of that supernova seen in 1054. At the nebula's center, a neutron star spins about 30 times a second, flashing its twin beams as a pulsar. These pulsars are like cosmic lighthouses, the remnants of stars that died in explosions yet continue to send a beacon of energy across space with each rotation. A neutron star is a stellar corpse, yes, but it is far from inert. It is dynamic, powerful, and astonishing. If a star's remaining core is extremely massive, above a certain threshold of a few times the Sun's mass, even the neutron star state cannot halt the collapse. The core implodes further and forms a black hole. A black hole is gravity taken to its ultimate extreme, an object so dense and compact that its gravitational pull becomes overwhelming. Not even light can escape from its vicinity once it strays too close. Around the black hole is an invisible boundary called the event horizon. Anything that passes this boundary, even light itself, is trapped and cannot return to the outside universe. The matter of the star collapses to an almost infinitely dense point at the center, a singularity, where our understanding of physics breaks down. To an outside observer, what remains is essentially a patch of pure blackness in space. The star itself has vanished from view, leaving only a powerful gravitational field behind. Yet black holes can make their presence known indirectly. If a black hole has gas, or a companion star nearby, its gravity can pull material into a swirling accretion disk around it. This infalling gas gets heated to extreme temperatures and emits powerful X-rays and other radiation before it slips past the event horizon. By detecting these X-rays, or by observing stars orbiting an apparently empty spot, astronomers can infer the presence of a black hole. In our own Milky Way galaxy, we have found several such stellar mass black holes by these signs. For example, one star might be seen rapidly orbiting an unseen partner that has the mass of a few suns, betraying a black hole's existence. Black holes represent a mysterious finale for the most massive stars, an endpoint where the star itself disappears from view, leaving behind only a warp in space and time, a gravitational footprint marking where it once was. We have followed the life of a star from its quiet birth in a nebula to its final fate as a white dwarf, neutron star, or black hole. It is a cycle of astonishing transformations. Yet in a sense, each ending is also a beginning. The material cast off by dying stars, those glowing nebula shells, supernova remnants, and even the faint wisps around white dwarfs, becomes the raw ingredients for new stars and new planets. In this grand stellar recycling, the universe renews itself. Each generation of stars enriches the cosmos further, sowing the seeds for more complex worlds and eventually for life. The carbon in our cells, the oxygen we breathe, the silicon in rocks under our feet, all were brewed in stars and spread through space to be incorporated in new cosmic creations. The lives and deaths of stars, as isolated as they may seem, are intimately connected to the broader tapestry of the cosmos. Stars light up galaxies, shape the chemical makeup of the universe, and leave behind exotic remnants that challenge our understanding of physics. As we step back and look at the galaxy as a whole, we see how these stellar stories weave into the larger cosmic narrative. In the next stage of our journey, we will venture beyond individual stars to explore grander structures and deeper mysteries, the galactic wonders that owe much of their splendor to the stars within them. The journey through the cosmos continues, ever deeper and ever more wondrous, as we leave the lives of stars and set our sights on the marvels of the galaxies they illuminate. As we venture deeper into our cosmic journey, a colossal star looms ahead in the darkness of space. At first, it is a distant ember, but as we draw nearer, it grows into an immense beacon, bathing the surrounding void in a coppery red glow. Its massive form dominates our view, like a cosmic sunset frozen in time. Unlike the steady golden light of our sun, this behemoth star burns tens of thousands of times brighter, its ruby light flooding the expanse. We drift closer, awed by its sheer size and presence, feeling as though we are in the company of a true celestial titan. This titanic star is a supergiant, one of the largest types of stars in existence. Our own sun, comparatively small and steady, would be a mere flicker beside this giant. If such a star replaced our sun at the centre of our solar system, its bloated surface would extend beyond the orbit of Jupiter. Mercury, Venus, Earth, and Mars would all be engulfed inside the star's glowing layers, lost in its fiery embrace. Imagining a planet that could orbit at a safe distance around this giant, the view would be surreal. The star would fill a vast portion of the sky, a bloated reddish orb hanging overhead. Daytime on such a world might be bathed in a perpetual dusk-like glow, the star's light more soft and diffuse than the sun's, but overwhelmingly present. Even at what we would call midnight, the horizon might still be aglow, the enormous star never truly setting, its diffuse light painting the sky in gentle amber tones. Stars like this defy our imagination with their scale. The most extreme hypergiant stars could fit billions of suns within their volume, or uncountable trillions of Earths. They are so immense that even light itself, which reaches Earth from our sun in only 8 minutes, would take hours to travel across the star's vast circumference. In their presence, familiar concepts like the size of orbits or the span of our entire solar system become insignificant yardsticks, dwarfed by the star's colossal bulk. Up close, its surface is a turbulent sea of boiling plasma. We see giant cells of hot gas rising and falling across the star's face, bubbles so large that each could engulf a planet whole. The star's outer layers are swollen and diffuse, glowing with a soft reddish-orange hue that betrays a cooler temperature than smaller, white-hot stars. Yet its total energy output is staggering, far outshining ordinary suns despite the cooler glow. It is a cosmic furnace burning through its fuel at an astonishing rate, racing through a life that will last only a few million years, a fleeting moment by cosmic standards. Such supergiants and hypergiants are exceedingly rare in our galaxy. Astronomers have identified only a scant few of them among hundreds of billions of stars. Born with dozens of times the sun's mass, they live fast and die young. In only a few million years, they burn through the nuclear fuel that smaller stars like our sun consume over the course of billions of years. These giants are spectacular but ephemeral characters in the cosmic drama, appearing briefly in the galactic story before fading in a final blaze of glory. Despite their scarcity, these stellar titans have a profound influence on their cosmic surroundings. Deep in their cores, they forge heavy elements through furious nuclear reactions, crafting the ingredients for planets and life itself. Their intense radiation and powerful stellar winds carve into the surrounding space, pushing and sculpting interstellar gas clouds. Sometimes, the shockwaves from their wind, or later explosion, can compress distant nebula, nudging new stars into being. In this way, they are both creators and destroyers, nurturing future worlds, even as they march toward an explosive end. Drawing nearer to the star, we notice it does not shine with a perfectly steady light. Its brilliance subtly rises and falls, as if the star is breathing. In fact, many of these giants pulsate like this, swelling and contracting in slow rhythms, a kind of stellar heartbeat that can take months or years for a single beat. At the same time, the star's atmosphere seethes and boils. Powerful stellar winds stream from its bloated surface, carrying away immense quantities of gas and dust. Over time, this escaping material forms a great smoky nebula encircling the star, a visible testament to the star's ongoing shedding of its own substance. Not long ago, a nearby red supergiant gave us a dramatic demonstration of this volatility. The star Betelgeuse, a crimson beacon marking the shoulder of Orion, suddenly began to fade in late 2019, growing noticeably dimmer in the night sky. For a moment, skywatchers around the world wondered if they were witnessing the prelude to a supernova, that perhaps Betelgeuse was on the verge of exploding. But after some weeks, the star slowly recovered its former brightness. Astronomers discovered that Betelgeuse had expelled a gigantic cloud of gas and dust from its surface, a billowing veil that temporarily obscured its light from our view. It was the first time humanity witnessed a star visibly shedding a portion of itself in real time. Betelgeuse had essentially belched out part of its outer layers, a quantity of material several times the mass of our moon. This cast-off cloud formed a veil of dust that dimmed the star's light from our perspective, before drifting away into space. The event was a startling reminder that even a seemingly steady star can change suddenly. One day, whether next year or centuries from now, Betelgeuse will indeed meet its fate and erupt as a supernova. In the meantime, its unexpected dimming gave us a precious glimpse into the turbulent life of a supergiant nearing death. Surrounding such a star, one can often find a complex tapestry of nebulous clouds, the cast-off layers that the giant has shed over time. Over centuries, each eruption and stellar cough piles more material into these expanding shells. Astronomers have observed enormous arcs and knots in these clouds, glimmering faintly in the star's reflected light. One famous hypergiant, VY Canis Majoris, is enveloped by a nebula hundreds of billions of kilometers across. Within these outflows lies matter on an almost unimaginable scale, rich enough to form thousands of Earth-sized planets. In these expelled layers, new molecules and dust grains condense out of the cooling gas. Elements like carbon, oxygen, and silicon, the raw materials for future rocky worlds, and even for life itself, are forged in the star and then scattered into space by its winds. Over time, these enriched clouds drift away and blend into the wider galactic medium. Eventually, they may coalesce into new stars and planets, seeding those nascent worlds with the chemical building blocks necessary for life to one day emerge. In a very real sense, we ourselves carry the ashes of long-dead giant stars within our bodies. Yet no matter how massive a star may be, its life cannot last forever. After millions of years of brilliance, the internal fires will eventually dim as the core's fuel is spent. In those final moments, gravity tightens its inexorable grip on the failing core. The balance that held the star aloft falters, and the Titan is left poised on the brink of collapse. Soon, perhaps without warning, this colossal star will meet a spectacular end. In one final act of cosmic drama, it will rip itself apart in a violent detonation, blazing forth as a supernova that outshines whole galaxies. Then, in a sudden flash, the long-expected catastrophe unfolds. Deep within the massive star, the core can no longer withstand its own crushing weight. In less than a second, it collapses inward, and an immense shockwave rebounds outward through the star's layers. The star explodes in a titanic supernova, unleashing more energy in that instant than 1,000,000 ordinary suns will emit in their entire lifetimes. In that moment, the dying star becomes ferociously bright. For a brief time, it can outshine an entire galaxy of billions of stars. The night sky, if we were watching from a nearby world, would suddenly be lit by a new gleaming star, perhaps even visible in the daytime. This cosmic flash is the supernova's opening act, a beacon announcing the death of a star across the cosmos. Throughout human history, such stellar outbursts have occasionally been witnessed in our own galaxy. Ancient astronomers once saw a new star appear where none had been before, so bright it could be seen even under the midday sun. For weeks it hung in the sky, captivating all who saw it, before slowly fading from sight. They could not have known then, but they were gazing at the dying embers of a supernova, the spectacular end of an unseen star that lived and perished light years away. Imagine witnessing such an event up close, not so close as to be harmed, but near enough that the sky lights up in an instant. For a brief period, the night would turn to day under the supernova's glow. A fierce point of light would hang in the heavens, casting shadows at midnight and outshining the moon. Ancient peoples who observed these new stars must have been astonished and perhaps fearful, unaware they were seeing the death cry of a distant sun. The supernova would slowly fade over weeks, but the memory of that unearthly brilliance would linger for a lifetime. The explosion is unimaginably violent. The star's outer layers are hurled into space at millions of kilometers per hour, crashing into any surrounding gas. A torrent of high-energy radiation and ghostly particles called neutrinos floods outwards as well. In the blink of an eye, the star that once was has been torn apart, replaced by an expanding cloud of incandescent debris. What remains of the star itself is compressed into an extraordinarily dense core, hidden in the brilliant chaos of the blast. While the collapse of massive stars is one common path to a supernova, it is not the only one. Even smaller, sun-sized stars can produce supernovae long after their normal lives have ended. Imagine a tiny, dense, white dwarf star, the leftover ember of a star like our Sun, siphoning gas from a companion star. If it hoards too much mass, it can ignite in a runaway thermonuclear explosion, obliterating itself in an instantaneous blaze. This too is a supernova, a cosmic bomb detonating in the darkness. Though born of a different process, such an explosion rivals the might of any produced by a collapsing supergiant. A supernova's brilliance and sudden appearance also make it a useful cosmic beacon. Certain types of supernovae shine with almost the same peak brightness every time. By comparing how bright they appear to us, astronomers can gauge their distances, using them as mileposts to measure the scale of the universe. In fact, such exploding stars have helped reveal the universe's expansion and the mysterious influence of dark energy, pushing galaxies apart. In the aftermath of the blast, a glowing nebula blossoms in the spot where the star once shone. The debris, superheated and racing outward, forms great filaments and tendrils that weave a cosmic tapestry across space. As the ejected gases expand and cool, they begin to shine in different colors. The faint reddish glow of hydrogen, the soft green of glowing oxygen, and traces of deep blue from other elements. Over years and centuries, this cloud of stellar ash billows outward, mixing with the surrounding interstellar gases, creating a beautiful and haunting remnant of the star's demise. One of the most famous of these supernova remnants is the Crab Nebula, the ghostly cloud left behind by a supernova observed on Earth nearly 1,000 years ago. Through a telescope today, we see the Crab Nebula as a tangle of delicate filaments spreading outward. It appears as a faint, misty patch in the constellation Taurus. But in long exposure images, it reveals rich detail and colour. At the nebula's centre lies a clue to the source of its energy. A tiny but incredibly energetic neutron star, the surviving core of the star that exploded. It is a poignant sight. The remains of a star scattered across the starscape, forming new patterns. The delicate filaments of the supernova remnant glow like cosmic gossamer, drifting through the darkness. What once was a solid star is now an ethereal nebula, a graceful memorial written in stardust. In time, this colourful cloud will fade and disperse, its material enriching the galaxy. But for now, it hangs in space as a testament to the star's final performance, beautiful, transient, and transformative. Supernovae are not just destructive, they are also creative on a cosmic scale. In the furious furnace of the explosion, atoms are smashed together to form new, heavier elements. Gold, silver, iodine, uranium, elements that the star could never make during its life, are forged in those brief moments of unimaginable heat and pressure. Meanwhile, more common elements like carbon, oxygen, and iron are flung out far and wide, seeding the galaxy with the materials to build future planets, oceans, and living beings. Every person listening now carries within them atoms made in the heart of an ancient supernova, scattered long ago into the cloud that formed our sun and earth. In this way, a supernova is both an ending and a beginning. The blast wave from the explosion can rush into nearby clouds of gas and dust, compressing them and stirring them to action. These disturbed clouds may eventually collapse under their own gravity, giving birth to new stars and planets. The heavy elements from the exploded star will be incorporated into those young suns and their worlds. Thus, the death of one star becomes the seed of many others, a cosmic cycle of rebirth that has been going on for billions of years. Yet even after the supernova's flash has faded and its debris spreads into space, the story is not over. Peering into the heart of the expanding nebula, we find an extraordinary survivor, the collapsed core of the star itself. Squeezed into an object only a few kilometers across, this remnant is unimaginably dense and strange. It is a neutron star, a city-sized ball of neutrons left spinning in the aftermath of the explosion. Though small in size, it is a beacon of extreme physics, often revealing itself as a pulsar, flashing beams of radiation like a cosmic lighthouse. Our journey now turns to explore these exotic remnants, the pulsars and magnetars forged in supernova fire. In the shattered aftermath of a supernova, the tiny core left behind defies ordinary experience. This core, a neutron star, packs the mass of an entire sun into a sphere scarcely a few tens of kilometers across. Imagine an object the size of a city, yet heavier than the sun. Its density is beyond comprehension. Atoms themselves can't survive the crush. The matter is squeezed so tightly that protons and electrons meld into neutrons, creating an immense ball of subatomic matter. The gravity on a neutron star's surface is unimaginably strong. If you could stand on such an object, though in reality nothing could survive there, you would weigh billions of times your earthly weight. A mere teaspoon of neutron star material would outweigh a mountain. It could be billions of tons. Under such crushing gravity, a dropped pebble would slam into the surface at a significant fraction of the speed of light. Everything about this remnant is extreme, yet this ultra-dense star remnant is far from inert. When the original star's core collapsed, it began to spin faster, much like a figure skater pulling in their arms, conserving its angular momentum. What was once a leisurely rotation of a giant star becomes an incredibly rapid spin for the tiny neutron star. Many newborn neutron stars rotate dozens of times each second, and the fastest known can whirl more than 700 times in a single second, faster than a kitchen blender. These spinning stellar cores are also highly magnetic, and from their poles they can emit beams of radiation that sweep around as the star spins. If one of those beams crosses Earth's line of sight, we perceive a pulsar, a star that seems to blink on and off with a precise rhythm. In reality, it is the lighthouse effect. Each time the beam sweeps past us, we catch a flash. These flashes can be astonishingly regular. Pulsars tick like cosmic clocks, some flashing multiple times per second with metronome consistency. To an observer with a radio telescope, they sound like steady pulses or beats from deep space. In fact, the first pulsar was discovered in 1967 by a young astronomer who noticed a strange repeating signal, unlike anything observed before. The pulses were so regular, arriving every 1.3 seconds with uncanny precision, that she humorously nicknamed the source LGM-1 for Little Green Men, half joking that it might be a transmission from an alien civilization. Soon, however, scientists realized the true nature of the signal. Not artificial, but a rapidly spinning neutron star, flashing its lighthouse beam toward Earth with every rotation. Since that serendipitous discovery, thousands of pulsars have been detected throughout our galaxy. They vary in their speeds and ages. Some are young and energetic, spinning dozens of times per second, while others are older and rotate more slowly. But all pulsars share that rhythmic blinking signal, a beacon that can travel across light years. By studying these signals, astronomers have gained insights into extreme physics. Pulsars have been used to confirm the existence of gravitational waves and to test the general theory of relativity under intense conditions. From afar, a pulsar would look like a faint, fast blinking star. In visible light, it might be barely noticeable, but through a radio telescope, the sky pulses regularly with its heartbeat. One can imagine floating in space, listening to the steady tick-tock of a pulsar's rotations, like the most precise clock in the universe. Each pulse is a reminder of a tiny stellar corpse spinning with incredible speed, sweeping its beam across the cosmos like a lighthouse on a dark sea. Pulsars are incredible, yet they are only one facet of the neutron star story. A small fraction of neutron stars are even more exotic. These are known as magnetars. Magnetars are neutron stars with magnetic fields so intense that they defy imagination. While a typical pulsar's magnetic field is already trillions of times stronger than Earth's, a magnetar's field can be another 1,000 times beyond that. These magnetic powerhouses are exceedingly rare. Only around 30 are known in our entire Milky Way, but they represent the most extreme magnetic environments in the universe. By contrast, a magnetar might not announce itself at all until a sudden eruption occurs. Most of the time it would appear as an unremarkable point in the darkness, undetectable without X-ray or gamma-ray instruments. Then, without warning, a tremendous flare would flash out, briefly outshining all other X-ray sources in the sky. If we had eyes for such energy, we would see a momentary burst of brilliance from an otherwise invisible spot, a cosmic magnet snapping and releasing pent-up energy. To put this in perspective, the magnetic field at Earth's surface, which gently swivels a compass needle, measures around half a Gauss. A regular bar magnet is about 100 Gauss. Just a regular neutron star has a magnetic field of 1 trillion Gauss. Magnetars are 1,000 times more powerful than that, with a magnetic field of a quadrillion Gauss. If a magnetar were within 1,000 kilometers of Earth, its magnetic field would distort the very atoms of our bodies and tear molecules apart. Even from a much greater distance, it could disrupt Earth's magnetosphere. Thankfully, the magnetars we know of are located thousands of light years away, so we are in no danger. But the mind reels at the raw power they possess. Magnetars don't announce themselves with gentle pulses like ordinary pulsars. Instead, they sporadically erupt with high-energy flares. The solid crust of a magnetar, an iron-hard surface under incredible tension, can suddenly crack in a starquake. Like a titanic earthquake, a starquake releases tremendous energy. When a magnetar's crust shifts even slightly, its magnetic field can unleash a burst of X-rays and gamma rays across space. These outbursts are brief, but ferocious. Astronomers have recorded a few such magnetar flares in our galaxy. The most powerful on record came from a magnetar known as SGR 1806-20. In December 2004, it released a flash of energy so intense that it briefly altered Earth's upper atmosphere from 50,000 light-years away. In a mere fraction of a second, this magnetar unleashed more energy than our Sun emits in 100,000 years. For that instant, it was the brightest extrasolar cosmic event ever detected by our satellites, a true monster flicker from across the galaxy. Pulsars and magnetars are astonishing cosmic lighthouses and magnets, pushing the limits of physics. But even these extreme objects have one final boundary they do not cross. They are made of matter that still resists complete collapse. There are some stars, however, so massive that nothing can halt their fall. When such a colossal star dies, no neutron star remains. The core continues to collapse inward without end, vanishing from view and creating a black hole. In the next stage of our journey, we approach these ultimate gravitational traps, the mysterious realm of black holes. For the most massive of stars, even the incredible densities of a neutron star are not enough to halt gravity. The stellar core collapses beyond any known limit, and a new kind of object is born, a black hole. In a black hole, gravity becomes overwhelming. All the mass is crushed into an infinitely small point, at least according to Einstein's theory. Surrounding that point is an invisible boundary known as the event horizon. Once anything, even light, crosses this boundary, it can never escape. The notion of an object so dense that not even light can escape dates back centuries in scientific thought. But it was through Einstein's general relativity in the early 20th century that the modern understanding of black holes emerged. For decades, black holes were thought of as theoretical oddities, solutions to equations, perhaps not actually found in nature. Many scientists doubted that such extreme entities could really form. Yet over time, evidence began to mount that the universe is full of black holes, quietly lurking in the darkness. The term black hole is a bit misleading. These aren't really holes at all, but rather regions of space filled with concentrated mass. They are black because no light escapes to reveal them, and in a sense they act like a hole, swallowing anything that comes too near. What truly makes a black hole is that event horizon. Get too close, cross that boundary, and escape becomes impossible. From outside, all we can see is the effect of the black hole's gravity on its surroundings. The first hints of real black holes were discovered through their effect on companion stars. In the 1960s, satellites detected intense X-rays coming from a seemingly blank spot in the constellation Cygnus. The X-rays were traced to gas superheated as it spiraled into an unseen object. That object, dubbed Cygnus X1, appeared to be a heavy, invisible mass pulling matter off a normal star, the telltale behavior of a black hole. This was one of the first strong clues that black holes were not just theory, but cosmic reality. Since then, many black holes have been found by indirect means. In our own Milky Way galaxy, a dramatic example lies at the core. Over years, astronomers watched stars near the galactic center whirl around an unseen object at astonishing speeds. By mapping these orbits, they deduced the hidden mass is about 4 million times that of the Sun, confined in a space no larger than our solar system. Nothing but a supermassive black hole could explain this. We now call this central dark mass Sagittarius A, the supermassive black hole at the heart of our galaxy. Perhaps the most striking evidence of black holes arrived only recently. In 2019, astronomers using a network of telescopes spanning the globe captured the first ever image of a black hole. This was not a traditional photograph, but a radio image showing the shadow of a supermassive black hole in a distant galaxy called M87. The image revealed a dark circle surrounded by a ring of glowing gas. Light from behind the black hole, bent around by its gravity. It was a stunning confirmation that these enigmatic objects are real and observable. A few years later, in 2022, the same technique produced an image of the black hole at the center of our own galaxy. At last, humanity had glimpsed the silhouette of the mysterious giant lurking in Sagittarius. These extraordinary images required combining data from radio observatories worldwide, effectively creating a telescope the size of Earth. Through this achievement, the once unseen and unknowable black hole has been made visible, a circular void imprinted on a swirling backdrop of light. Visualize for a moment what a black hole might look like up close. The black hole itself would be invisible, a hole in space. But around it, the infalling gas forms a luminous swirling disk. This accretion disk glows white-hot, wrapping around the black hole. As we draw nearer, light warps in bizarre ways. The disk's far side appears to bend up and over the dark center, due to the black hole's gravity deflecting the light. The black core sits like an ink-black sphere against the brilliance, a circular shadow where the disk's light vanishes. It is an eerie, beautiful sight, like an eye of darkness surrounded by a fiery halo. Interestingly, black holes are not always black. When they feed on surrounding matter, they can become the engines of immensely energetic phenomena. Gas and dust spiraling into a black hole form an accretion disk, heated to incandescence by friction and gravitational forces. This disk can glow brightly in X-rays and other light. In some cases, black holes also fire out narrow jets of particles at nearly light speed from their poles. These jets can extend for thousands of light years, announcing the black hole's presence. Some of the brightest objects in the cosmos, quasars and radio galaxies, are powered by supermassive black holes devouring matter, their jets and disks blazing across space. Black holes also reveal themselves through the subtle tremors of spacetime. In 2015, scientists detected gravitational waves, faint ripples in the fabric of spacetime itself, emanating from the merger of two distant black holes. As the black holes spiraled into each other and coalesced, they sent out a shudder through the universe, which sensitive instruments on Earth picked up. This discovery not only confirmed a prediction of Einstein's theory, but also provided a new way to hear black holes merging in the dark. Since then, dozens of such mergers have been recorded, giving us a completely different window into the hidden lives of black holes. The environment around a black hole is a strange realm where our intuitions break down. Space and time themselves are warped by the extreme gravity. If you were to approach a black hole in a spaceship, you would see some bizarre effects. From a safe distance, you might watch objects falling toward the black hole appear to slow down as they near the event horizon. Their light would stretch to redder and redder wavelengths, a phenomenon called gravitational redshift, until they fade from view. To you, it would seem as though anything that falls in takes an eternity to actually cross the threshold. On the other hand, for an object, or unfortunate astronaut, that is doing the falling, things would feel very different. As they plunge closer to the black hole, tidal forces, the difference in gravity between their head and feet, increase dramatically. For a small black hole, these forces could stretch the falling object grotesquely, a process darkly nicknamed spaghettification. The astronaut would be pulled into a long, thin ribbon as they near the horizon. In a larger, supermassive black hole, the tidal stretching near the event horizon would be gentler, so one might actually drift across that boundary without immediate harm or even noticing the crossing, though there would still be no way back once inside. Even with these advances in observing black holes, many mysteries linger. We can measure their mass, watch their effects on nearby matter, and even image their shadow, yet we cannot see what happens inside. What lies beyond the veil of the event horizon remains inaccessible. The laws of physics as we know them may falter in those extreme conditions. As we prepare to delve deeper into the enigma of the event horizon itself, we stand at the boundary between knowledge and the truly unknowable, the threshold that guards the black hole's secrets. The event horizon of a black hole is the ultimate boundary, the dividing line between the observable universe and a realm forever cut off from our view. It's not a physical surface, but rather a spherical frontier encircling the black hole. Once anything passes through this invisible barrier, it is as good as gone from our universe. No signal, no light, no information can escape back across that boundary. In essence, the event horizon is the one-way door to the unknown. For an outside observer, the event horizon appears to mark the end of space as we know it. It's a boundary of ignorance. Beyond it, we cannot see or obtain any information. If a star, a planet, or even a beam of light crosses that threshold, it vanishes from our view as though the universe simply edited it out. The horizon thus separates the known from the unknowable. We can only speculate about what transpires inside, because no message can ever be sent back to enlighten us. In a way, the term event horizon is evocative of ancient times when sailors spoke of the horizon as the edge of the known world. In ages past, our ancestors stood on distant shores, gazing at the ocean's horizon and wondering what lay beyond. Today, our horizons are cosmic and metaphorical. The event horizon of a black hole is the new edge of the unknown, a boundary we cannot yet cross, even in theory. It challenges us, much as the great horizons of Earth once challenged explorers to push onward. Curiously, from our viewpoint, objects approaching an event horizon never quite disappear in finite time. They seem to slow and fade, their light stretched to invisibility as they asymptotically approach the horizon. It's as if the event horizon is a frozen film of everything that ever fell in, captured at the brink. Some physicists have speculated that, in a sense, all the information about those objects may remain encoded on the horizon itself. The black hole might only appear to swallow information, while in reality, the memory of everything is stored on its boundary, a holographic imprint of the fallen matter. The true mystery deepens when we bring quantum physics into the picture. In the 1970s, physicist Stephen Hawking made a startling theoretical discovery. Black holes are not completely black after all. Through quantum processes at the event horizon, black holes can slowly emit radiation, now known as Hawking radiation. This happens because the vacuum of space is teeming with particle-antiparticle pairs popping in and out of existence. Near the event horizon, one particle of such a pair can fall into the black hole, while the other escapes, making it seem as if the black hole is radiating particles. Hawking's insight implied that black holes have a finite lifespan. By emitting this faint heat, they slowly lose mass and energy. Over incredibly long timescales, far longer than the current age of the universe for black holes of stellar size. A black hole will eventually evaporate away entirely, fading into a final burst of radiation and then nothingness. It is a mind-boggling conclusion. Something once thought eternal and all-consuming can actually dissipate like a water droplet evaporating in the sun. This realization led to one of the deepest puzzles in modern physics, known as the black hole information paradox. If a black hole can evaporate completely through Hawking radiation, what happens to all the information about the objects that fell inside? According to quantum physics, information about a system, the specific details of its particles and their states, should never be destroyed, even if the form of the matter changes. But if a black hole disappears, does the information it swallowed simply vanish from the universe? Hawking himself initially argued that the information was indeed lost forever, hidden behind the event horizon and gone with the black hole's evaporation. This bold claim shook the foundations of physics because it suggested a fundamental law: the conservation of information might be violated. Over the years, debates raged among physicists. Many came to believe that somehow, in ways not yet fully understood, the information must be preserved. Perhaps it is encoded in the Hawking radiation in a highly scrambled form, or stored on the event horizon's surface until the very end. In recent years, theoretical breakthroughs have hinted at a resolution. Ideas from string theory and a principle called holography suggest that all the information that falls into a black hole might be encoded on its two-dimensional surface, much like a hologram stores a 3D image on a flat film. If true, this means that nothing is truly lost. It's just that the information is smeared on the event horizon and gradually released back through subtle correlations in the Hawking radiation. Stephen Hawking himself eventually conceded that information might escape after all, in forms too subtle for our current technology to detect. Still, a complete understanding of these processes remains elusive. To truly know what happens at and beyond the event horizon, to follow information through a black hole and back out again, we likely need a unified theory of quantum gravity, a new physics that merges Einstein's relativity with quantum mechanics. Such a theory remains one of the holy grails of science. Until then, the event horizon stands as a symbol of the frontier of our knowledge, a literal and metaphorical boundary we strive to cross with thought and imagination. The unknowable region beyond the event horizon has also inspired speculation beyond physics textbooks. Science fiction and theoretical science alike have pondered, could a black hole be a gateway to elsewhere? Some solutions of Einstein's equations hint at hypothetical tunnels in spacetime, wormholes, that might connect black holes to other universes or distant parts of this universe. It's an enticing idea. Perhaps falling into a black hole might spit one out somewhere or someone else. But so far, wormholes remain purely speculative, and even if they did exist, surviving a journey through one is another matter entirely. Having explored the darkest depths and greatest extremes, from colossal stars to supernovas, pulsars, and the mysteries of black holes, we find ourselves at a turning point in our cosmic journey. We pull back from the brink of the abyss and gaze outward once more, Beyond the realm of collapsed stars lies a magnificent tapestry of cosmic structures waiting to be explored. Our voyage will next sweep us into the grandeur of galaxies and the wonders of the larger universe, where new mysteries and splendors await among the stars. Our journey continues from the stellar wonders we explored previously and moves into a broader realm. In the silent darkness of space, we drift further from our familiar sun. Up until now, our journey has lingered among individual stars and nebula, marveling at their births, lives, and deaths. Now our view begins to widen. As we float higher and higher above the galactic plane, the scattered stars below us start to merge into a faint, glowing band. This is the edgewise view of our own galaxy, and it beckons us to explore its grand structure. From our vantage point in the Milky Way's outskirts, the galaxy stretches out like a broad, silvery river of light. Ancient sky watchers once looked up at that hazy band arching across the night sky and spun stories about its origin. Some imagined it as milk spilled from the heavens, others as the glowing path of departed souls. In truth, this ghostly band is composed of countless distant stars whose light blends together. It is the combined glow of our galactic home, seen from within. If we could travel outside the Milky Way and gaze back, we would see a magnificent spiral-shaped disk floating in space. The Milky Way is a barred spiral galaxy, a flattened disk of stars with a bright central bulge and graceful spiral arms winding outward. Through its center runs a thick bar of stars, a glowing spine that anchors the spiral arms. These arms unfurl from the ends of the bar, swirling outward like the curving trails of a cosmic pinwheel. Our galaxy spans roughly 100,000 light-years from edge to edge, an immense island of stars, gas, and dust. Imagine rising high above the galactic plane, leaving behind the sun and its neighbors. As you soar into intergalactic space and look down, the Milky Way's pattern would slowly reveal itself. The diffuse band of light would condense into a defined form, a spiral disk with graceful arms curving around a bright core. The dark rifts we see from Earth would be seen for what they are, great lanes of dust cutting through the starlight. From this godlike vantage, you could see our entire galaxy at once, its hundreds of billions of stars united into one swirling form against the blackness of space. Such a perspective is beyond our physical reach for now, but through scientific understanding, we can picture it in the mind's eye. Embedded within the spiral arms are stellar nurseries and young star clusters, while older stars dominate the central bulge. The spiral arms are not solid structures, but patterns where stars are slightly denser, like traffic jams of stellar light slowly winding around the galactic center. Here, vast clouds of gas and dust gather. Within these clouds, new stars ignite, adding their brilliance to the flowing arms. Between the arms lie quieter regions with fewer bright stars, giving the spiral its characteristic banded look when seen from afar. Our sun resides in one such quieter spur between the Milky Way's major spiral arms. We live in a minor arm called the Orion Spur, nestled between the larger Sagittarius and Perseus arms. At around 25,000 light-years from the galactic center, our solar system drifts in the suburbs of the galaxy. When we look up on a clear summer night toward the constellation Sagittarius, we peer toward the heart of the Milky Way. In that direction, densely packed stars and clouds obscure our view of the core, but their collective glow paints the sky with a milky luminescence. At the very core of the galaxy, a mystery lies hidden behind veils of dust. There, the stellar density grows extreme. Millions of stars crowd into a region only a few light-years across. This central hub of the Milky Way is a bulging sphere of old, reddish stars, some of them among the earliest born in our galaxy. And at its precise centre, invisible to optical telescopes, lurks a supermassive black hole. Known as Sagittarius A, this gravitational giant holds about 4 million times the mass of our Sun. It anchors the galaxy, its unseen influence gently steering stars in orbits around the galactic heart. Though we cannot see the black hole itself, we witness stars whipping around an apparently empty centre at astonishing speeds, a sure sign of an enormous mass lurking there. Surrounding the bright core, the Milky Way's disk is relatively thin compared to its diameter. Our galactic disk is only about 1,000 light-years thick in the region of the Sun, though it thickens nearer the centre. Within this disk, stars orbit the centre in a majestic galactic rotation. Even our Sun, with all its planets in tow, races around the galactic centre at roughly 200 kilometers per second. Yet the gulf of space is so vast that one complete orbit takes on the order of 230 million years. In the time since the dinosaurs roamed the Earth, our Sun has barely completed a single revolution around the Milky Way's core. Looking beyond the visible, our galaxy is enveloped in an even larger, fainter halo of stars and mysterious, invisible matter. This galactic halo extends far above and below the flat disk. It contains sparse sprinklings of old stars, including entire clusters of ancient stars that swarm around the galaxy. And permeating this halo is something we cannot directly see: dark matter. This unseen mass vastly outweighs all the stars and gas we can observe, forming an invisible scaffold that holds the galaxy together. As stars orbit the galaxy, they move faster than expected from visible matter alone, tipped off by the gravitational influence of this dark halo. Though the nature of dark matter remains unknown, its presence is a deep mystery that adds to the mystique of our galactic home. From inside the Milky Way, determining its structure took decades of careful observation. We are like ants trying to map the shape of a forest while deep inside it. Early astronomers struggled to understand the galaxy's layout because dust clouds in the disk block distant starlight, hiding the galaxy's true extent. In the late 18th century, William Herschel tried to map the Milky Way by counting stars in different directions, concluding the Sun lay near the centre of a roughly disc-shaped system. He did not realize that thick dust clouds were obscuring distant stars, leading to an incomplete picture. It was only in the early 20th century that the true scale became clear. Using globular star clusters as mileposts, astronomer Harlow Shapley determined that these clusters formed a vast halo, centered not on Earth or the Sun, but on a point deep in the constellation Sagittarius. This discovery revealed that the Milky Way's core, its true center, lay far away, and that our Sun occupied a quiet suburb in the galactic outskirts. Bit by bit, our perspective shifted from thinking our solar system was the universe's hub to understanding that we are just one part of a much larger galactic structure. In the mid-20th century, astronomers turned to radio waves and infrared light to peer through the dust. By mapping emissions from cold hydrogen gas in the disk, they uncovered the Milky Way's spiral arm structure and confirmed that our galaxy is a barred spiral like many we observe in the cosmos. Yet even today, some details remain uncertain. For instance, astronomers debate exactly how many major spiral arms our galaxy has, and new discoveries continue to refine our picture. The Milky Way still holds secrets, quietly awaiting those who seek to unravel its story. Yet even with unanswered questions, the broad strokes of our galaxy's portrait are clear and awe-inspiring. We live inside a gigantic pinwheel of stars. Its swirling arms cradle stellar nurseries and young blue suns. Its central bulge shelters a massive black hole and ancient stars. An invisible halo of matter cocoons the entire galaxy, binding it with gravity's gentle force. When we gaze up at the Milky Way on a dark night, we are gazing along the disk of this magnificent structure from within, peering through a tiny keyhole at a universe of wonders. Far from diminishing our sense of place, understanding the Milky Way's structure enhances the wonder. We realize that our sun is just one star among hundreds of billions, all bound together in a gravitational dance. The pale band of light overhead is no mere cloud. It is the integrated light of distant suns circling the same center. Our galaxy, in turn, journeys through space as a coherent whole, spinning slowly like a glowing whirlpool against the cosmic darkness. It is a humbling and mesmerizing realization. Everything we have ever known lies on a small world, orbiting an ordinary star, drifting in the outskirts of a majestic spiral galaxy. We have gone from seeing that hazy band as mere milk in the sky to understanding it as our galaxy. And yet, much about the Milky Way remains elusive. There is poetry in knowing that our home galaxy, in all its immensity, is just one of billions. The Milky Way is our cosmic home, and yet it is merely one chapter in the universe's grand story. To truly appreciate its place, we must step back and look at the galaxy not just as a whole, but also at the communities of stars within it. Scattered throughout our galactic disk and halo are special groupings of stars, stellar families born together, shining together. These star clusters dot the galaxy, each a tiny microcosm of stars with its own tale. By exploring these clusters, we move one step closer to understanding the rich tapestry of the Milky Way and the company it keeps in the universe. Not all stars wander the galaxy in solitary splendor. Many are born together in groups, sharing a common cosmic cradle. These groupings of stars, known as star clusters, are like stellar families. They drift through the galaxy as units, bound by mutual gravity, at least for a time. Scattered across the Milky Way, star clusters come in different types and sizes. Some are loose and youthful, like restless children, while others are ancient and tightly bound, like wise elders, gathering closely for warmth. If you gaze up on a clear night in late autumn and find the constellation of Taurus, you might notice a tiny, misty patch of light near the bull's shoulder. With the unaided eye, it appears as a small, dipper-shaped smudge. Point a telescope toward it, and that misty glow resolves into a glittering collection of bright blue stars. This is the Pleiades, a famous open star cluster, often called the Seven Sisters. It's a group of young stars that form together from the same cloud of gas. In the Pleiades, hundreds of sibling stars are bound in a loose, shimmering congregation about 400 light-years from Earth. They shine with a blue-white brilliance, illuminating faint wisps of the very nebula from which they were born. The sight of the Pleiades is a gentle reminder that stars, including perhaps our own sun, often emerge in families. Across cultures, this cluster has inspired legends. The Greeks saw it as 7 divine sisters, and other peoples imagined it as a gathering of birds or lost souls in the night. Such stories hint at how these stellar gatherings have captivated human eyes for millennia. Open clusters like the Pleiades are common in the spiral arms of the Milky Way. They are relatively small groups of stars, dozens, hundreds, or sometimes a few thousand at most, born at nearly the same time. Astronomers have catalogued more than 1,000 open clusters in the Milky Way and suspect the actual number could be many times higher, hidden by dust. Each is a snapshot of stellar youth, offering clues about how stars form and evolve together. These clusters are often irregular in shape, with stars scattered in a loose assembly rather than packed tightly. Because they form in the galaxy's disk from giant molecular clouds, open clusters tend to be young. Many are just a few million to a few 100 million years old, mere infants or adolescents on the cosmic timescale. They also typically still contain traces of the gas and dust that gave birth to their stars, though much of it gets blown away by stellar winds and radiation once the stars ignite. As open clusters orbit within the bustling disk of the galaxy, they face a violent environment. Tidal forces from the Milky Way's gravity, along with close encounters with other stars, gradually pull these clusters apart. Over tens or hundreds of millions of years, the cluster's member stars often wander off one by one, escaping the weak gravitational grip holding them together. Eventually, many open clusters disperse entirely, their stars becoming part of the general background population of the galaxy. In fact, our Sun itself is believed to have formed in an open cluster billions of years ago. Since then, that birth cluster has long since dissolved, its stellar siblings scattered far and wide. Somewhere out in the Milky Way, the stars that were once the Sun's nursery mates now journey separately, indistinguishable from any other stars around them. Though we cannot identify those long-lost siblings now, they have merged into the vast sea of stars that surrounds us. Yet while they last, open clusters are splendid laboratories for understanding stars. Within a single cluster, all the stars share a similar age and chemical composition, having formed from the same cloud. The main difference between them is their mass. This makes open clusters valuable to astronomers. By comparing the colours and brightness of cluster stars, scientists can test theories of stellar evolution. On a more human level, these clusters inspire wonder. Each is like a stellar nursery frozen in time, a snapshot of siblings growing up together before eventually parting ways. In contrast to the youthful, sparse open clusters, the galaxy also hosts another, very different family of star clusters. Far out in the Milky Way's halo and swarming around the galactic centre are the globular clusters, so named because of their roughly globular or spherical shape. Picture a snow globe filled with stars instead of snowflakes, thousands upon thousands of points of light packed densely toward the centre. A globular cluster is a gravitationally bound ball of stars, and it is truly a sight to behold. These globular clusters are ancient, among the oldest structures in the galaxy. Many of them formed around the same time the Milky Way itself was taking shape, roughly 10 to 12 billion years ago. Each globular cluster contains anywhere from tens of thousands to, in some cases, millions of stars, all held tightly together by their mutual gravity. In the core of a globular cluster, stars are so densely packed that they could be only a fraction of a light year apart from each other. If you were in a planet inside such a cluster, your night sky would be ablaze with countless close suns on all sides. The collective light of these stars often gives globular clusters a hazy, golden glow when seen through telescopes, an effect of the many red giants and aging stars within them. Consider what the night might look like from deep inside one of these globular clusters. On a hypothetical planet near the core, hundreds of thousands of suns would crowd the sky. Night would be aglow with countless stars, far brighter than any in our earthly sky, bathing the darkness in a perpetual twilight. It would be a spectacular, crowded heavens, perhaps too bright for any creature there to ever see a truly dark night. One famous example of a globular cluster is Omega Centauri, visible from the southern hemisphere. To the naked eye, it appears as a fuzzy star, but through a telescope, it blossoms into a crowded sphere of sparkles. Omega Centauri contains millions of stars and is so massive that some astronomers suspect it might be the remnant core of a small galaxy consumed by the Milky Way long ago. In the northern hemisphere, clusters like M13 in Hercules provide a similar spectacle on a slightly smaller scale. Hundreds of thousands of stars densely bundled in a ball. Viewed through a backyard telescope, a bright globular cluster like M13 in Hercules appears as a hazy round patch at first. But with patience, one can resolve its glittering core. Countless stars huddled together, giving the impression of a fine sprinkling of cosmic sugar against the dark. These ancient clusters circle the outskirts of our galaxy, like a halo of bejeweled satellites. Globular clusters mostly inhabit the halo of the Milky Way, orbiting the galactic center on highly elongated paths that can carry them far above and below the galactic disk. Currently, around 150 globular clusters are known to belong to our galaxy, and there may be more hidden on the far side behind thick dust clouds. These clusters are like fossils of the early universe. They're stars bearing witness to a time when heavy elements were scarce. The stars in globular clusters typically have low metallicity, meaning they contain few of the heavier elements that younger stars, like our Sun, have. This is because they formed before successive generations of supernova explosions had enriched the galaxy with elements like carbon, iron, and oxygen. In a way, studying the stars in globular clusters is akin to peering back into the conditions of a young universe. Despite their great ages, globular clusters can still experience change. Stars in such crowded quarters occasionally interact. In such cramped conditions, stars frequently gravitationally interact. Some may even exchange partners or collide, giving rise to unusual systems, such as blue straggler stars that appear younger than the cluster's age, or binary systems with neutron stars and black holes that churn out X-rays. Others may transfer mass in binary systems, creating exotic phenomena like low-energy X-ray binaries or millisecond pulsars that astronomers have detected emanating from these clusters. In their dense cores, it's even been proposed that intermediate mass black holes might lurk unseen, swallowing any star that ventures too close. The globular cluster environment is harsh, yet many of these clusters have survived intact for eons, weathering the tides of the Milky Way's gravity and the occasional brushes with other clusters or passing stars. Star clusters, both open and globular, provide a profound sense of the scales and dynamics within our galaxy. They show us that stars have siblings and communities, and that those communities live out lives of their own. Some clusters are born, live a youthful existence, and drift apart, while others persist nearly as long as the galaxy itself. When we see a star cluster through a telescope, whether the tight ball of an ancient globular or the sprinkle of a young open cluster, we are witnessing a stellar gathering that has its own story. A beginning when the stars first ignited, a middle as they shine together, and in some cases an ending as the group disperses. There is something comforting in knowing that even in the vast cold of space, stars often travel with companions. These clusters are like cosmic family gatherings, transient perhaps, but beautiful and meaningful in their time. Having explored the Milky Way's structure and its star clusters, we can appreciate that our galaxy is an immense and lively system. Our galaxy, vast as it is, does not float alone in the cosmos. It has neighbours, other galaxies moving through space in our general vicinity. Some are small and bound to us like companions, while others are giant galaxies in their own right, separated by the vast gulfs of intergalactic space. The local group is our cosmic village, and like any community, its members interact and change over time. With Andromeda drifting closer each day on a cosmic timescale, we see that even galaxies live in relationship with one another, setting the stage for future transformations. To truly grasp our galaxy's place in the universe, we must meet these galactic neighbours and learn about our local community in the cosmos. The Milky Way, vast as it is, does not drift through space in isolation. Like an island surrounded by an archipelago of smaller isles, our galaxy is part of a small cluster of galaxies bound together by gravity. All around us in the darkness, at distances almost too immense to fathom, lie our galactic neighbours. Some are diminutive dwarf galaxies, cosmic companions that orbit the Milky Way like tiny moons around a planet. Others are large spiral galaxies, comparable to our own, each with its own swarm of stars and mysteries. Together, they form a local cosmic family, a collection of galaxies journeying through the universe as a loose-knit group. On a clear night in the southern hemisphere, one might notice two faint, cloud-like patches adorning the sky. These nebulous smudges, visible to the unaided eye, puzzled observers for centuries. Today we know them as the Magellanic Clouds, two dwarf galaxies orbiting near our Milky Way. The larger of the pair, the Large Magellanic Cloud, LMC, lies about 160,000 light-years away. The smaller, the Small Magellanic Cloud, SMC, is a bit farther at around 200,000 light-years. To the naked eye, they appear as wispy fragments of the Milky Way's glow, detached and floating off to the side. But telescopes reveal them to be galaxies in their own right, each containing billions of stars. The Magellanic Clouds are irregular in shape, lacking the stately spiral structure of larger galaxies. They are thought to be distorted by interactions, both with each other and with the Milky Way's gravitational pull. In these dwarf galaxies, stars and clusters are strewn about in asymmetrical patterns. The Large Magellanic Cloud, LMC, being the nearer and bigger one, even hosts regions of furious star formation. One such region, the Tarantula Nebula, is a colossal cloud of gas and newborn stars near the LMC's heart. It is the most active star-forming region in our galactic neighbourhood, a brilliant hub where massive stars are being born at a prodigious rate. If the Tarantula Nebula were as close to us as the Orion Nebula in our own Milky Way, it would cast visible shadows on Earth's night sky. So intensely does it glow. Such marvels within the Magellanic Clouds remind us that even these smaller galaxies can be abuzz with cosmic activity. For a long time, the true nature of the Magellanic Clouds remained a mystery. To the astronomers and navigators of old, these glowing patches were curiosities, perhaps nearby nebulae or clusters just at the edge of the Milky Way. It wasn't until the 20th century that scientists measured their great distances and realized the clouds lay far outside our galaxy. At last, the Magellanic Clouds were recognized as separate, orbiting companion galaxies to the Milky Way. Now we understand that the Magellanic Clouds are gravitationally bound companions of the Milky Way, engaged in a slow cosmic waltz with our galaxy. Over time, they have likely orbited and swung past the Milky Way multiple times, each encounter tugging and stretching them, leaving behind streams of stars and gas. In fact, a long ribbon of gas known as the Magellanic Stream trails behind them, evidence of the gravitational interplay between these dwarfs and our larger galaxy. Someday in the distant future, the Magellanic Clouds may even merge with the Milky Way entirely, adding their stars to the larger galactic population. Beyond these close-knit companions, there are other, more distant galaxies that share our cosmic neighborhood. In addition to the Magellanic Clouds, the Milky Way is orbited by dozens of even smaller dwarf galaxies. Most of these are faint and diffuse, harder to spot amid the starry backdrop. Some, like the Sagittarius dwarf, are actually in the process of being torn apart by our galaxy's gravity, their stars strewn into tidal streams. The most prominent external galaxy is the Great Andromeda Galaxy, often simply called Andromeda, after the constellation in which it resides. On a dark, moonless night in the northern hemisphere, Andromeda can be glimpsed with the naked eye as a faint, elongated smudge of light. It doesn't look like much at first glance, but that smudge is the combined glow of an entire galaxy of stars. Even though it appears as a dim blur, Andromeda actually spans a width in the sky, several times that of the full moon. Its light is just spread thin across a huge area. Over the coming billions of years, that blur will slowly grow brighter and larger as Andromeda edges nearer to us. The Andromeda Galaxy is about 2.5 million light-years from the Milky Way, so far that its light takes 2.5 million years to reach us. Yet in the scale of the universe, Andromeda is one of our nearest major neighbors. Andromeda is a spiral galaxy, much like our own, but it is larger and holds even more stars. While the Milky Way contains on the order of a few 100 billion stars, Andromeda may boast 1 trillion or more. In structure, Andromeda has expansive spiral arms and a bright central bulge. Observations suggest it, too, has a bar structure at its core and a supermassive black hole anchoring its center. Through telescopes, we see swirling bands of stars and dark dust lanes, as well as numerous globular clusters dotting its halo, over 400 such clusters, significantly more than our Milky Way. In many ways, Andromeda can be thought of as a sister to the Milky Way, slightly larger and possibly a bit more massive, but fundamentally similar in composition and form. Imagine telescoping the distance to Andromeda. As you draw nearer, the faint smudge would expand into a grand spiral of stars. If you could move swiftly across the void between our galaxies, that faint blur would grow in size and detail. You'd begin to resolve spiral arms and bright nebulae within Andromeda, until eventually you were close enough that its full majesty filled your view, a sprawling metropolis of stars stretching over 100,000 light-years. Accompanying Andromeda are its own retinue of satellite galaxies. Just as our Milky Way has the Magellanic Clouds and other small satellites, Andromeda has dwarf companions like M32 and M110, which are visible as fuzzy blobs near Andromeda's glow in telescopic images. There is also the Triangulum Galaxy, M33, a spiral galaxy somewhat smaller than the Milky Way, located not far from Andromeda in the sky. Triangulum, at around 3 million light-years away, is another member of our local galactic family and may be gravitationally bound to Andromeda. It has well-defined spiral arms, but no central bar, and it too is forming new stars in colourful nebulae along its spiral arms. All these galaxies, the Milky Way, Andromeda, Triangulum, the Magellanic Clouds, and dozens of smaller dwarf galaxies, together constitute what astronomers call the local group. In total, the local group contains over 50 galaxies, mostly tiny dwarfs, bound in this relatively small pocket of the universe. The Milky Way and Andromeda are the two dominant giants, each with their entourage of satellites. The gravitational dance of the local group keeps its members slowly orbiting a common center of mass. From an even broader perspective, Our local group itself is part of a larger assembly called the Virgo supercluster, but that is a scale we will explore a bit later. What's truly remarkable is how until the early 20th century, we didn't even know for certain that other galaxies existed beyond the Milky Way. The Andromeda galaxy was long referred to as the Andromeda Nebula, presumed to be a cloud or cluster within our own galaxy. It wasn't until astronomer Edwin Hubble measured the distance to Andromeda by observing special bright stars called Cepheid variables that we learned the truth. Andromeda was far outside the Milky Way, an island universe of its own. This finding settled a great debate of the time about the spiral nebulae and whether they were part of our galaxy or separate galaxies of their own. The revelation that the universe contained myriad galaxies like our own was humbling and exhilarating for science and stargazers alike. This discovery expanded our understanding of the cosmos enormously. The universe was suddenly understood to be filled with countless galaxies, not just our single Milky Way. Now, as we gaze out, we see that the Milky Way is one of many galaxies in a vast cosmic ocean. Our nearest big neighbour, Andromeda, is drawing nearer by the force of gravity, destined to have a profound encounter with us billions of years from now. The local group itself drifts within an even larger community of galaxies. In the silent depths of space, galaxies occasionally reach out and touch one another. The future collision of the Milky Way and Andromeda will be a dramatic event, but it is by no means unique. Galaxies throughout the universe often interact and merge in a slow gravitational ballet. To understand what awaits our galaxy and what shapes many galaxies' histories, we must look at these titanic collisions, the moments when galaxies meet and pass through each other, forever changing their shapes and stars. In the vast darkness between galaxies, gravity quietly weaves its influence. When two galaxies draw near, they begin a slow, majestic dance that can last hundreds of millions of years. Unlike the sudden crash one might imagine, a galactic collision is more like a gradual mingling of starry swarms. As the galaxies approach each other, their mutual gravity stretches and distorts them. Tidal tails of stars stretch far into space, arcing out from each galaxy like cosmic taffy being pulled. Slowly, the galaxies swing through one another, pass by, and might loop around for another encounter. Over time, these encounters cause the galaxies to merge into a new, combined system. What emerges from the union is a reshaped galaxy, sometimes a larger spiral, often an elliptical with a new form and character. One of the most striking aspects of galactic collisions is that individual stars almost never collide head-on, despite the unimaginable scales involved. A star is so small compared to the distances between stars that during a merger, the stars of one galaxy simply sail past those of the other. For the most part, they thread through each other's ranks like grains of sand in a cosmic hourglass. A collision between galaxies, then, is not like a smash-up of solid objects, but rather a gravitational ballet. The real chaos happens not from stars crashing, but from the collective gravitational forces. Gas clouds slam into other gas clouds, triggering bursts of star formation, and orbits of stars are thrown into new patterns. Imagine witnessing such an event. Two enormous spiral galaxies swirling into one another. As they first interact, you might see the orderly spiral arms become tangled. Gas and dust clouds compress under the gravitational tug, igniting brilliant new stars. In the galaxy's cores, supermassive black holes, each lurking at the heart of its respective galaxy, begin their own slow spiral toward eventual union. Eventually, those two black holes will merge into an even larger one, likely unleashing a burst of energy and gravitational waves as they settle into a single beast. Over a long time, perhaps after a few passes, the two galaxies coalesce. Their shapes lose distinct identity. The once graceful spirals may become a bloated, amorphous glow of billions of stars. In many cases, the end product of a major merger is an elliptical galaxy, a large ball of stars with little remaining spiral structure. The violence of the merger can stir up so much gas and trigger so many supernovae that much of the gas is expelled, leaving an elliptical galaxy that has mostly old stars and not much raw material for new ones. Our own Milky Way, as serene as it appears on a human timescale, is not immune to such cosmic encounters. In fact, it has quietly been engaging in a slow collision for billions of years, the cannibalization of smaller dwarf galaxies. Even now, our galaxy is in the process of merging with multiple tiny companions. One example is the Sagittarius dwarf galaxy, a small collection of stars that has been stretched into a long stream by the Milky Way's gravity. These stellar streams, arcing high above the galaxy's disk, are remnants of galaxies the Milky Way has torn apart and absorbed over time. Our galaxy's halo is full of such ghostly remains, evidence that galactic mergers are an ongoing part of its evolution. And on the horizon of time lies an even grander event, a collision between titans. The Milky Way and the Andromeda Galaxy are on a slow-motion collision course. Though separated by 2.5 million light-years at the moment, their mutual gravity is drawing them together. In about 4 billion years, the two great spirals will begin to noticeably disrupt each other. From Earth, if by then someone is here to look up, Andromeda will no longer be a faint patch of light. It will swell to dominate the night sky, a swirling neighbour growing larger with each passing eon. As the galaxies draw close, new stars will light up the sky from bursts of star formation. Over an immense span of time, the disks of the Milky Way and Andromeda will intermingle and merge. Stars that once belonged to one galaxy will find themselves in the new merged galaxy, taking up orbits in a reformed system. During this encounter of the Milky Way and Andromeda, it's likely that our Sun and its planets will survive relatively unscathed, drifting into the merged galaxy along with billions of other stars. The night sky, however, would change dramatically. As the galaxies first collide, new stars will light up the sky from bursts of star formation. Over millions of years, constellations would warp into unrecognizable shapes as our star's position relative to others shifts. It might be a fantastical scene. New star clusters igniting like fireworks, stellar streamers linking the two galaxies across the sky, and perhaps the spectacle of brilliant variable stars flaring as gas and dust are compressed in shockwaves. What once was a familiar sky would become utterly alien and alive with novel sights. Eventually, after perhaps another 2 billion years of interactions, the merger will be complete. The two spirals will settle as one large galaxy. Some scientists predict it might be a giant elliptical dubbed Milkomeda. The majestic spiral patterns of both original galaxies may be gone, replaced by a huge, diffuse glow of countless stars. Our Sun will then inhabit a very different cosmic city than the orderly spiral disk it was born in. Galactic collisions are not rare in the cosmos. In fact, they have played a major role in shaping the galaxies we see today. In the distant past, when the universe was younger and galaxies crowded closer, collisions happened more frequently. Giant galaxies grew by cannibalizing smaller ones in a cosmic snowball effect, and galactic interactions were key in shaping the modern universe. Many galaxies bear the marks of past mergers, some giant ellipticals, which dominate the centers of galaxy clusters, are thought to be the result of multiple mergers stacked on top of one another, building up truly enormous collections of stars. Astronomers often observe peculiar galaxies, ones with warped disks, double cores, or long tidal tails of stars flung far out, and recognize these as signs of a past collision. We can even catch galaxies in the act of merging. For example, one dramatic collision can create a ring galaxy when one galaxy plunges straight through another, like a stone through water. The impact ripples out a circle of stars. Other collisions fling out bridges of stars tens of thousands of light years long, connecting galaxies momentarily before gravity draws them back. For instance, the antennae galaxies, a famous pair of colliding galaxies, are entwined in a merger right now. In images of the antennae, long streamer-like tails of stars extend from the galactic cores. Brilliant knots of young blue stars mark regions where the collision has triggered intense star formation. Other cosmic collisions have produced ring-shaped galaxies or galaxies with long bridges of stars between them, stellar arcs pulled out by gravity. Each new observation of these phenomena reinforces how creative and transformative these mergers can be. Each galactic collision unfolds over a time frame so vast that no single observer could watch it from start to finish. But by surveying the sky, we see different mergers caught at different stages, like snapshots of a dance frozen at various moments. Some pairs of galaxies are just starting to tug at each other. Others have already passed through once and are leaving the scene of their first encounter, trailing stellar debris. Still others have nearly finished merging, their cores coiling around each other to become one. Through these snapshots, we piece together the narrative of these cosmic mergers. Despite the drama they entail, galactic collisions are a natural part of the universe's evolution. They are one way that galaxies grow and change. A small galaxy might merge into a larger one, contributing its stars and gas, and perhaps inducing a new wave of star birth. Two equals might collide and transform into a new kind of galaxy altogether. And even in destruction, there is creation. The chaotic gravity of a merger that disrupts old structures also creates new ones, like star clusters formed from smashed-together gas clouds. It's awe-inspiring to realize that even destruction on this scale is a creative force in the universe, forging new stars and new galaxies from the remnants of old. Having witnessed the spectacular violence and creativity of colliding galaxies, we can step back even further. We have looked at individual galaxies and their interactions, but these are still just pieces of a bigger puzzle. When we zoom out to truly large scales, we see that galaxies themselves form parts of much larger structures. The Milky Way and Andromeda's dance is just one small event within a vast network of galaxies. To see the grand design of the cosmos, we must look at how galaxies are arranged on the largest scales, the cosmic web that stretches across the universe. Beyond the scale of galaxies and their mergers, there lies an even grander pattern. If we could pull our vantage point far, far back, so far that entire galaxies shrink to tiny glimmering dots, a remarkable structure would emerge. Galaxies are not scattered randomly through the universe. Instead, they are arranged in a vast cosmic web, a latticework of filaments and clusters intertwined across space, with immense voids in between. In this web, galaxies congregate along thin threads that intersect in nodes, rather like the silk strands of a spider's web meeting at dew-laden junctions. The image is breathtaking. Millions upon millions of galaxies lining up in great chains that span hundreds of millions of light years, outlining colossal empty spaces where few galaxies roam. The existence of this cosmic web became evident as astronomers mapped the positions of galaxies over decades. When plotted on an extremely large scale, the distribution of galaxies revealed patterns: long filaments and walls of galaxies, and vast black voids where hardly any light shines. It looked almost like a cosmic foam, or the neurons of a gigantic brain, an intricate network with immense voids and dense nodes. One famous early finding was the Great Wall, an immense sheet of galaxies stretching across hundreds of millions of light years. More recently, astronomers have identified even larger formations, like the so-called Great Attractor and colossal walls of galaxies extending over 1 billion light years, pushing the limits of what we thought possible. By the late 20th century, redshift surveys like the Sloan Digital Sky Survey created ambitious 3D maps of hundreds of thousands of galaxies, vividly confirming this foam-like architecture. It seems that on the grandest scales, matter in the universe has gathered into this sponge-like arrangement. Dense regions and empty regions, repeating over and over. Our own cosmic neighborhood is part of this pattern. The local group, the cluster of galaxies containing the Milky Way and Andromeda, is on the outskirts of a much larger collection of galaxies known as the Virgo cluster. The Virgo cluster, in turn, is one lobe of an even larger entity called the Virgo supercluster, a broad congregation of many galaxy clusters. Astronomers discovered that the Virgo supercluster itself is part of an even larger structure called Laniakea. Laniakea is our home supercluster, encompassing the Virgo supercluster and neighboring groups, defining the region whose galaxies share a common gravitational destiny. These nested structures illustrate the hierarchical organization of the universe. At the intersections of the cosmic web's filaments sit the most massive structures of all, galaxy clusters containing hundreds or thousands of galaxies bound together. If we journeyed along one of these great filaments, we would drift past galaxies every few million light years, like sparse streetlights in an empty desert. It could take billions of years to traverse from one cluster to another along these routes. When we finally arrived at a massive cluster, a hub of the cosmic web, we would find ourselves amid thousands of galaxies swarming together, a busy metropolis in the emptiness. One such example is the Coma cluster, a great cluster of galaxies, millions of light years across, anchoring a node in the web. Between these nodes stretch filaments where galaxies are fewer but still present, forming bridges between clusters. And between the filaments lie the voids, enormous dark expanses spanning tens of millions of light years where galaxies are exceedingly scarce. In these nearly empty volumes, night would fall eternal and darkness would reign. If you were floating in the middle of one of these voids, you might see nothing but darkness in all directions. The nearest galaxies so distant they'd be mere pinpoints, or entirely beyond the horizon of visibility. It would be a solitude unlike any other, the loneliest expanse one can imagine. Some voids are so vast that we wondered if they contained any matter at all, or if they were truly empty. We now believe that even within voids there are traces of matter, perhaps wisps of gas or dark matter, but far too little to spark the formation of many stars or galaxies. What caused such a grand pattern to form? The roots of this grand cosmic pattern lie in the early universe. Not long after the Big Bang, matter was almost evenly distributed, but not perfectly so. Tiny fluctuations, slight differences in density, were present in that primordial fireball. Over billions of years, gravity worked on those ripples, magnifying them. Regions that started just a bit denser than average exerted a stronger gravitational pull, drawing in more matter from their surroundings. As they grew denser, their gravity grew stronger still, snowballing over time. Meanwhile, regions that were slightly less dense lost matter to the gathering clumps around them, becoming ever more empty. This process gave rise to the cosmic web we see today. We can still see evidence of those original fluctuations in the cosmic microwave background, the faint afterglow of the Big Bang, which shows tiny temperature variations corresponding to the seeds of future galaxies. Dark matter, the mysterious invisible substance that makes up most of the universe's mass, is thought to be a critical thread in weaving this cosmic web. Though we cannot see dark matter, it forms a kind of scaffolding on which normal matter, the atoms that make up stars and galaxies, collects. Computer simulations of the universe's evolution, which include dark matter and gravity, naturally produce a filamentary cosmic web, strikingly similar to what we observe. This tells us that our picture of how structure forms is on the right track, even if we still don't fully understand the nature of dark matter itself. Standing back and considering the cosmic web, one cannot help but feel a sense of awe. On these scales, our Milky Way is just a tiny node on a thin strand among millions of others. As we contemplate this nearly unfathomable structure, from the tiny scales of moons and planets to the vast tapestry of the cosmic web, we begin to sense the unity of the cosmos. On such scales, even a giant galaxy like our Milky Way becomes just an insignificant point of light. Each level is connected to the next, forming part of an ongoing cosmic story. From the Milky Way's gentle glow in our night sky to the great walls of galaxies stretching through the universe, it is one magnificent continuum. Yet even the cosmic web is not an infinite structure. It has boundaries in the sense that it fills the observable universe we can see. Beyond the horizon of what our telescopes can detect, the pattern likely continues, but we are limited by the speed of light and the finite age of the universe. Meanwhile, the accelerating expansion of the universe, driven by a mysterious force called dark energy, is stretching these filaments further apart. Over tens of billions of years, distant clusters outside our local supercluster will recede beyond visibility. The cosmic web we see today is a snapshot in time, a stage in an ever-evolving universe. What we can observe already encompasses tens of billions of light years. Within that vast expanse, estimates suggest there are perhaps 2 trillion galaxies, all woven into the fabric of this immense cosmic web. Looking at the cosmic web also reveals a remarkable fact. On the very largest scales, the universe appears homogeneous. The web repeats over and over such that, if you zoom out far enough, every region of space looks statistically similar, a cosmic foam with comparable filaments and voids. We reside in one tiny corner of this grand design. Our local supercluster is but one filament among countless others threading through space. From the gentle glow of our home galaxy, we ventured to star clusters where suns gather, then outward to meet neighboring galaxies. We witnessed how galaxies collide and merge, and finally, we gazed upon the cosmic web tying everything together. Each step outward revealed a new layer of structure, yet also deeper mysteries. Our journey through the stars and galaxies has taken us from Earth's familiar sky to the edge of the observable universe. We have marveled at stars, nebulae, galaxies, collisions, and the grand cosmic web. Still, there remain profound mysteries and questions. How did this vast universe begin? What will be its ultimate fate? And are there more wonders beyond what we can see? In the cosmic vista we've explored, each answer often leads to new questions, inviting us to continue the exploration. The cosmos, with all its billions of galaxies woven into a tapestry of light and darkness, still holds countless secrets. As we float in the quiet of intergalactic space, on the threshold of knowing and unknowing, our journey is far from over. The universe always has more to reveal.